Hello and welcome. My name is John Horvath, and the title of my presentation today is From Wetlands to Wings and a River Ran Through It. This is a presentation about the 77 years and counting geotechnical history and all that we've learned from it at the John F. Kennedy International Airport in New York City. My motivation and inspiration for making this presentation is the observation over the last few years that Kennedy Airport represents a really unique geotechnical case history. It's more like a controlled laboratory experiment in foundation design and construction than the typical case history that we read about or hear about in a presentation. There are several reasons for this, I think. One is that the airport has been in existence for 77 years now. Construction began in 1943. And technologically, that covers the transition from the slide rule era to the microprocessor era. The Kennedy Airport property is owned by the City of New York, but for its entire existence, it has had the same operational lessee, an organization that we refer to here in the New York City area as the Port Authority. The more formally named is the Port Authority of New York and New Jersey. Prior to 1972, it was the Port of New York Authority. So it's had the same operator for its entire existence. Despite the relative size of the airport, about 5,000 acres, 2,000 hectares, much of the airport site has remarkably uniform subsurface conditions, and therefore the foundation requirements are pretty identical throughout the airport property. Because this site has always been a commercial airport, it's had the same basic structure types: passenger terminals, hangars, maintenance facilities, control towers, elevated roadways. And these structures have been built over and over again in the airport history, often at the same locations. Just within the last year or so, a major makeover of Kennedy Airport was proposed, and hopefully we will see this begin within the next few years. So once again, I think we'll see a rebuilding, repurposing of the airport property. Well, when you put all these facts together, this allows us to trace different geotechnical and foundation engineering technologies in several parallel tracks. And although these are specific to Kennedy Airport, as you'll see in my presentation, they really have global applicability. So although this is a presentation about Kennedy Airport, I think that engineers around the world will find that there are things I will talk about that are applicable to the specific conditions and structures that they may be involved in. Probably the single most important thing is that although nature, of course, has not changed at Kennedy Airport, how we as civil engineers and geologists have investigated and reinterpreted nature has changed tremendously over time. And because of these changing reinterpretations, the design requirements for foundations have changed tremendously in the last 77 years as well. And this allows us to see how all of the stakeholders involved, from the owners, foundation designers, material suppliers, construction contractors, have put their minds together and collectively and synergistically met these changing foundation demands in a cost-effective manner. Here is an outline of my presentation. This is a relatively lengthy presentation, and you may find it useful to break up your viewing of the presentation into these various sections that I've illustrated here. When I think of Kennedy Airport, two things come to mind. One is that it is a story of towers and a story of change. In the history of Kennedy Airport, there have been several towers. The current control tower, when it was built in 1992, was the tallest in the world at over 300 feet, about 100 meters above the ground surface. Rather interestingly, now in 2020, it is not even in the top 10 in the world, certainly not even the tallest in the United States. When it was built, it was twice the height of the 1950s era tower. That was a signature structure at Kennedy Airport for several decades. The original control tower, when the airport opened for commercial operation in 1948, was of course very modest by today's standards, but typical for that era. And while a lot of people know about these various towers, I suspect very few people know about this tower, which actually dates back to the late 19th century. Of course, it was not an aircraft control tower, but the important thing is that the foundations for this tower remain to the present time buried under the Kennedy Airport landfill. So the location of this tower, or the remnants of this tower, is very important in this discussion, because certainly as we move forward in the coming years to rebuild Kennedy Airport once again, I'm sure that stakeholders involved in that work would like to make sure that they don't run into obstruction from past construction. The one thing that all of these towers have in common is they're supported on piles. Let me talk about now how Kennedy Airport came to be. Let me get my pseudo laser pointer started here. Okay. All of the three commercial airports in the New York City area, Kennedy, Newark, and LaGuardia, have several things in common. They were all built on marine tidal wetlands of bodies of water that are connected to the Atlantic Ocean. And as such, they have all required driven pile foundations to support structures, including very tall light poles. Rather interestingly, they all have one person in common, and that is Fiorello LaGuardia, who was mayor of New York City for about a dozen years in the first half of the 20th century. Newark Airport was the first airport constructed in the New York City area. And of course, it has changed many times over the years to what we see at the present. It was Mayor LaGuardia's dissatisfaction with the fact that there was no commercial airport in New York City that led to the development of what we now call LaGuardia Airport. In fact, at the time, if you bought an airplane ticket to New York City, you actually landed at Newark Airport, and that did not sit well with Mayor LaGuardia. LaGuardia Airport, of course, has gone through its own series of changes over the years, and in fact, at the present time is just finishing up a major makeover of that airport. When that airport opened, it was known as New York Municipal Airport, since renamed LaGuardia Airport. Well, LaGuardia Airport had no sooner opened than it was deemed to be insufficient for New York City's growing air traffic needs, so people started to look for alternatives. There were apparently some rather fanciful suggestions made at the time. This rather remarkable structure would have been located on the west side of Manhattan Island. Here's the Hudson River, here's the Empire State Building, Central Park, the East River. As you can see, it would have been a multi-story structure serving a passenger ship terminal, multiple levels of dining and shopping, and just to make life interesting, an airport runway on the roof and airport hangars on some of the upper floors. Of course, this was never built. The alternatives that were seriously looked at were much more mundane. Here you see Mayor LaGuardia during the planning of what turned out to be Kennedy Airport, and the site chosen on the periphery of Jamaica Bay in Queens housed several minor private airports at the time. So here's the location of Kennedy Airport. It was built on the periphery of Jamaica Bay, and as you can see, Jamaica Bay is a tidal connection to the Atlantic Ocean. What is now Kennedy Airport went through several name changes during its planning, construction, up to the present. Many years ago, it was referred to colloquially by native New Yorkers like me as simply Idlewild, after a local place name. These days, it's referred to simply as Kennedy or JFK to New Yorkers. I will refer to it using the acronym JFKIA in this presentation. I now want to talk about the site geology and topography, which is quite complex. And as I indicated at the outset, certainly one of the areas where we've seen tremendous change in reinterpretation over time. Highlight a slide that I showed at the beginning of the presentation to make this point. More than anything else, the geological conditions at Kennedy Airport have been reinvestigated and reinterpreted over time. And it's been this reinterpretation that, to a very significant extent, has dictated and driven the changes in foundation design at the airport for the last several decades. So Kennedy Airport really is a case history where the reinterpretation of nature, again, nature hasn't changed, but how we've reinterpreted nature has really driven all the technological change we've seen at Kennedy Airport over the last several decades. And this reinterpretation at Kennedy Airport has affected not only the airport, but the entire New York City metropolitan area, and to a certain extent, the entire east coast of the United States. The understanding that we can have seismic conditions here on the east coast of the United States, something that we began to appreciate only in the 1980s, really has changed foundation design along the entire east coast of the United States in the last several decades. So again, although we're focusing on Kennedy Airport and the reinterpretation there, certainly this is quite typical of the reinterpretation that we've seen through a good part of the United States the last several decades. Well, let's begin by talking about the overall geological setting with the physiographic province. Much of the east coast of the United States lies within what is called the Atlantic Coastal Plain Physiographic Province. That province actually begins here at the southern edge of New York City, where we have Kennedy Airport. So Kennedy Airport is at the very northern limits of the Atlantic Coastal Plain Physiographic Province. The bedrock conditions that are typical of this physiographic province is that you have sloping crystalline bedrock, often quite old. The bedrock underneath New York City is in places estimated to be approximately 1 billion years old. And this sloping bedrock transitions from continental plate to oceanic plate for the Atlantic Ocean. In this distorted isometric map, you have an idea of how rapidly bedrock changes within the New York City area. Kennedy Airport is off here towards the southeast, and what this is showing is that throughout much of Manhattan Island, bedrock is at or above the ground surface. You'll notice a very prominent gap here in the bedrock, and this is the location of the largest known geologic fault within Manhattan Island, the so-called Manhattanville or 125th Street fault. We'll see a little bit that there are quite a few brittle geologic faults throughout the New York City area. We don't see bedrock exposed within Brooklyn, a little bit in Queens, although not shown here in the Bronx. Bedrock is very prominent at or above the ground surface in the Bronx. And we do see bedrock above the ground surface in parts of Staten Island as well. This is a generic geologic profile through the Kennedy Airport area. We see the sloping crystalline bedrock, and within the Kennedy property, the bedrock is roughly 700 to 1,000 feet below sea level, 200 to 300 meters below sea level. We talk about now the pre-Pleistocene soils. Characteristic of the Atlantic coastal plain province is that you often have multiple strata of varying geological age. Geologists often map these strata as poorly lithified sedimentary rock. However, to geotechnical engineers, these are really stiff clays and very dense sands. So one does have to be a bit careful at times when you look at a so-called bedrock geologic map, that very often these older, very stiff, very dense soil deposits are mapped as rock. They are not rock in the traditional civil engineering sense. Within the Kennedy Airport property, all of these pre-Pleistocene soils are Cretaceous age, and although they do not figure into the foundation engineering at Kennedy Airport, these are very significant strata throughout Long Island, especially for water supply purposes. A rather interesting reinterpretation in recent years has to do with the Hudson River. Of course, the Hudson River is not a true river throughout much of its length. It's actually a fjord or a tidal estuary. And here is the present course of the Hudson River between Manhattan Island and northeastern New Jersey. We've known for many decades now that at one time the Hudson River flowed on the backside of the Palisades Ridge in New Jersey. And this is the reason why in this area that we call the Jersey Meadowlands, why we see valleys that have been carved into the underlying Triassic sandstone and shale that may be as much as 300 feet or about 100 meters below sea level. Of much more recent interpretation is the fact that the Hudson River apparently once flowed through Queens, and we see that it actually flowed underneath the site that is now Kennedy Airport. Here you can see the contours of this ancestral channel of the Hudson River. They're typically 200 to 300 feet, up to 100 meters below sea level. They do not affect the foundation engineering at all at Kennedy Airport, but they are still an interesting geologic artifact. And again, one of the many ways that we have reinterpreted geology in the New York region in recent decades. Well, let's talk about the Pleistocene geology, which really dominates the foundation engineering conditions at Kennedy. For the most part, the Atlantic coastal plain province was not directly affected by Pleistocene glaciation. And this is because all of the Pleistocene glaciers ended somewhere within the greater New York City area. So in general, direct Pleistocene effects are not seen along this part of the east coast of the United States. However, as we'll see, they are very prominent under New York City in general and Kennedy Airport in particular. In terms of the overall Pleistocene stratigraphy, again, if we look at our generic geologic profile at Kennedy Airport, the Pleistocene deposits total about 200 feet, 60 meters in thickness. And there are three major strata. We have the Geotechnical gravel, which 100 or so years ago was fresh flowing artesian conditions. It is now brackish due to over withdrawal over many, many decades by humans. We've simply pumped more water out of the Geotechnical than nature has put back in. Above the Geotechnical, we have the Gardener's clay, which tends to be fairly thin and discontinuous, but you will encounter it in deep borings that are drilled within the Kennedy Airport site. So if you drill some relatively deep borings, these borings will frequently terminate in a very stiff, hard, dark gray clay. That's the Gardener's clay. Of much more significance is the upper Pleistocene deposits that total about 125 feet, 40 meters in thickness, technically known as the upper glacial aquifer. These are important because they have been and continue to be the foundation bearing stratum for all structures at Kennedy Airport. So as I indicated in an earlier slide, any major foundation at Kennedy Airport for buildings, roadways, light rail, transit, tall light towers requires a deep foundation. All of these foundations are going to be bearing within the upper glacial aquifer. For a long time, the glacial history of New York City was thought to be understood, but now the more we learn, the more we realize that we don't know very much. For a long time, it was thought that only one glacier affected the New York City area. It was the thought of one Wisconsin-age glacier did it all, stopped in the middle of Long Island, and all of the Pleistocene soils that we see throughout the area are the result of that one glacier. While we now understand that's simply incorrect, there have been multiple distinct glacial events. Some researchers think as many as 5, and each of them has left their distinct mark on the region. And one of the primary ways that geologists tell the different glaciers apart are by the soils they left behind. As we know, as glacial ice moves across the landscape, it will break off pieces of the underlying bedrock and grind that rock up into ever smaller particles, boulders, cobbles, and then the smaller soil-sized particles, gravel, sand, and silt. Some of the minerals will be transformed into clay minerals. So for glaciers that flowed from the northwest to the southeast, these tend to leave soils that are dark red to maroon in color, and that's because much of the rock that was picked up and broken into soil particles was from these Triassic shales and sandstones and conglomerates that we find throughout northeastern New Jersey and Rockland County in New York State. And these rocks have a very distinctive dark red maroon color. On the other hand, glaciers that flowed from the northeast to the southwest picked up bedrock from the igneous rocks on the east side of the Hudson River, upstate New York, Connecticut, and left behind soils that are much lighter in color. We now interpret that several of these older glacial events were Illinoian, even pre-Illinoian in age. So they are spread out throughout the Pleistocene. One of the more important reinterpretations in recent years is that we've always known that there were several terminal moraines on Long Island. The Harbor Hill and Roanoke Point define the north shore of Long Island. The Ronkonkoma terminal moraine defines the center spine, if you will, of Long Island. Well, we now understand that there was a third, as yet unnamed terminal moraine, much of which now lies offshore of Long Island within the Atlantic Ocean. But the reason that this is quite important to us is because, as you can see, it is believed to have gone directly under the Kennedy Airport site. And I'll also point out that this newly identified terminal moraine goes right through Coney Island. And I highlight Coney Island because this area has seen a lot of high-rise building construction in recent years. And one of the things we found in Coney Island is over a relatively short distance, you could get a surprisingly significant change in subsurface conditions. And it's quite possible that part of the reason for this may simply be because this terminal moraine went right through Coney Island. Let's talk about the geomorphology that these glaciers has left behind. If we look at an older map of Long Island before extensive human development, one of the things that immediately jumps out if we look at the south shore of Long Island, and this is a distance of over 100 miles, almost 200 kilometers, we notice that the area around Jamaica Bay which is where Kennedy Airport is currently situated, is geomorphologically different. It looks different than the rest of the South Shore. In particular, we could see a semicircular area, and I've called this the Jamaica Bay salient. So we see a geomorphological shape to the topography that we don't see in the rest of the South Shore. So the question then becomes how this come to be, how this anomaly come to be. Another anomaly is if we look at the stream pattern. These black lines that you see here, trending from northeast to southwest, these are all streams within the South Shore of Long Island. And again, we notice that the stream pattern extends across the entire South Shore, but does not extend into the area around Jamaica Bay and the Jamaica Bay salient. Again, begs the geological question, why? Well, this Jamaica Bay salient is now interpreted to be the end result of what we call the Connecticut lobe and the Hudson lobe of the Laurentide Glacier moving down from Canada. And what these two lobes of the glacier represent is, as the glacial ice moved across what is now New England and upstate New York, you had one path that followed the Connecticut River Valley, and we call this the Connecticut lobe. You have another path that followed the Hudson River Valley, and we call this the Hudson lobe. And you see that they met head-on here, and by doing so, kind of mutually prevented the other one from advancing further. The net result is what I call the last glacial maximum reentrant that occurred during the most recent Wisconsin Age glacier. And this now relates to the unnamed third terminal moraine that, again, most of it lies offshore of Long Island, but we see that part of it curves around directly under the Kennedy Airport site, and as I pointed out earlier, under Coney Island as well. Well, we now put all of these facts together and we interpret them to mean that Jamaica Bay itself has never been covered by a glacier. Because again, we had the glacial ice came down in kind of a pincer type of movement. These two advances of the glacier blocked each other, with the net result is that the glacial ice never extended within Jamaica Bay itself. So the importance for Kennedy Airport is that it means that there's a rather sharp transition of no glacial ice, terminal moraine, and glacial ice within the airport property in both a nominally north-south and east-west direction. So this certainly complicates our interpretation of the Pleistocene geology at Kennedy Airport quite a bit. As part of this, the stratigraphy at Kennedy Airport, Bering stratum is being reinterpreted. The former, or still is, the upper glacial aquifer is now interpreted as being much more complex than we thought. Specifically, it's now recognized that the upper glacial aquifer is not one stratum, but three distinct geologic formations. The Merrick, which is a sand and gravel, the Wantaw, and the Belmore, which is another sand and gravel. But we see that this intermediate Wantaw formation, in older geological literature, it's called the 20-foot clay, is composed of organic soils, evidence of a marine environment. These red marks here are areas where the Wantaw formation has been identified. Again, here you see Coney Island. And again, it begs the question, if this unnamed terminal moraine ran through Coney Island, maybe this is the reason we see it here, but not here. I've looked at hundreds of borings at Kennedy Airport in my almost 50-year professional career, and I can tell you that you will see evidence of this Wantagh formation in some borings. It tends to be very thin, very discontinuous. I think part of the reason we've identified it more is because typically when we make a boring, we take a standard split spoon sample every 5 feet or every 1.5 meters. So it's very easy to miss a very thin, discontinuous soil layer. As we do more cone penetrometer soundings throughout Kennedy Airport, the Wantagh formation should show up more readily. And I highlight the Wantagh formation and the fact that it is an organic silty clay because historically we've only been concerned about the Holocene organic clay that is much shallower when it comes to foundation design, as I'll show you in a minute. Well, if we now move from the Pleistocene to the Holocene, limiting ourselves to the pre-site development of Kennedy Airport for the time being. Very typical of the Atlantic Coastal Plain province is that the coastal areas are covered by organic soils, and that's because sea level has risen after the glaciers by about 120 meters or 400 feet. Here you see a plot of sea level over the last million years. If we focus on a more recent 140,000 year time frame, we see that the most recent time when sea level was at its low point, we call this the last glacial maximum of the Wisconsin, roughly 15,000 or so years ago. And you can see that sea level was down about 120 meters, 400 feet, as I indicated. And by the way, MIS just stands for Marine Isotope Stage. It's a metric that geologists and others use to define climate episodes. So if we bring ourselves up to 1891, when this edition of the U.S. Geological Survey topographic map was created, we see that the general area where Kennedy Airport was eventually constructed, we see the open water of Jamaica Bay. Jamaica Bay is tidal range of about 5 feet, 1.5 meters. We see very classical marine tidal marsh deposits, organic clay with surficial peat. We see a number of tidal sloughs cutting through the area, and these tidal sloughs then transition to upland streams. I do want to highlight this rail line going across Jamaica Bay that was built around 1880. This exists at the present time as part of the New York City subway system, and I point this out because this is a constant geographical feature that we can use to orient ourselves in some of the maps and photographs I'll be showing you subsequently. So I'm pointing this out now. Well, we see here with the dashed yellow lines, this is the approximate outline of the current airport property. As you can see, some of it was in open water, most of it was in the tidal wetlands, a bit of it around the edges was upland areas. The so-called central terminal area where all the passenger terminals are located, you see here, this is underlain primarily by marine tidal marsh deposits. A couple of geographical features that we can use to orient ourselves in future slides. This is Idlewild or Long Neck Point, and this is Long Neck Creek. You could see Long Neck Creek kind of cuts right through the middle of the present day central terminal area, continue to the upland area of adjacent Queens. This Idlewild Point is going to be an interesting feature that we'll talk about quite a bit more. Well, let's talk about seismicity, because this is certainly the single most important reinterpretation of geology in the last several decades, not only at Kennedy Airport, but the New York City metropolitan area in general, and as I said earlier, the east coast of the United States in general. We now recognize that there's a potential for relatively significant earthquakes throughout the entire east coast of the United States. And as a result, in new construction and rehabilitation, we need to take this into account. Let's first talk about the regional history. This graphic was produced by a research team at Lamont Doherty Earth Observatory at Columbia University some years ago. And it shows all of the known, as best as can be reconstructed, epicenters of significant earthquakes. You see a scale here between 1677, which is roughly when European settlement of this region started, through 2004. And here's Kennedy Airport here. The black lines are known geologic faults, brittle faults. One of the problems with East Coast seismicity in general is that compared to other parts of the United States, other parts of the world, where very often you could see a fault trace on the ground surface, it's often difficult to do so in the East Coast of the United States, simply because these brittle faults in the underlying crystalline bedrock have been covered over by significant thicknesses of more recent soil deposits. But you can see the most significant known geologic fault throughout this region is the Ramapo Fault. You see cuts through here, and that's why you see the sharp change in color change in this map. Well, looking closer at Kennedy, we see that in 1884 there was a magnitude 5.2 event, 1937 a magnitude 3.5 event. To see how these rate on the overall assessment of earthquakes in this region in the last several hundred years. This tabulation was another outcome from other researchers at Lamont Doherty, and it's a tabulation of the largest earthquakes near New York City. Again, here you see Kennedy Airport. And we find that this 1884 5.2 event was the largest that is believed to have occurred. And I highlight this because once we start getting into the low 5 range, magnitude range, certainly in the East Coast of the United States, we're getting into a range where we could see some fairly modest physical damage of structures, and also in the right conditions, we could see seismic liquefaction. Of interest is the fact that this 5.2 does not appear to have been an outlier. As best as can be determined, about 140, 150 years earlier, there was an event of similar magnitude. The exact location of that event is not known with certainty. It tends to be plotted somewhere here in the Hudson River between Manhattan Island and northeastern New Jersey. But as noted here, there's a lot of uncertainty with that. But the point still is that we could see what we draw from this, the conclusion we draw from this, is that perhaps every 100, 150 years, we could expect an earthquake in the low 5 range within the New York City area. And if you do the math, as they say, you could see that we're pretty much due for one of these in the near future here in the New York area. The 3.5 event that was close to Kennedy Airport falls somewhat down on the list. I will point out that Manhattanville or 125th Street fault I talked about cuts across here, and as you could see, there were some fairly recent small events, enough to be felt, that were epicentered on that fault. So although the New York City area is well away from an active tectonic plate boundary, due to past tectonic activity over the last billion years, there's quite a system of brittle faults throughout this region, and therefore we do have potential sources for, reasonably significant seismic events. Well, the engineering consequences of this seismicity should have the direct shaking, which means that nowadays we have to design for lateral loads at foundation level and appropriate structural response. More significantly for Kennedy Airport is the likelihood of liquefaction, and something that's not talked about very much, tsunami potential. And the support for both of these comes from what we call paleoseismological evidence. If you're not familiar with the term paleoseismology, this is a study area within geology where seismologists look for evidence of past earthquakes in various soil features and then try to put a time frame or date on when these occurred and also what magnitude of earthquake may have caused this. New England has been studied a lot for this purpose, simply because they have earthquakes that are similar, somewhat larger than we see in the New York area. People often talk about the Cape Ann event of 1755, which is somewhere around a magnitude 6. So somewhat larger than the 5.2 that we see down here in the New York City area. Newburyport, Massachusetts has seen a lot of this paleoseismological study. It's an area that is not been developed. It's a national park, so the surface conditions have not been changed by human activity. And both liquefaction and possible tsunami features have been found in this area. And these are the sort of things that seismologists look for. Here you can see a sand dike, the light-colored sand. This is evidence of seismic liquefaction as the sand cut through the darker-colored horizontal soil layers. And this particular event is estimated to have occurred in the last 3,000 years or so. Quite surprisingly, there's evidence, suggestion of tsunamis. Physical evidence that's very similar to tsunami evidence we have seen in the Pacific Northwest, for example. And this is estimated to have occurred in the last 2,000 years. Well, I now want to talk about how the Kennedy Airport site was developed. Basically, I want to discuss how we've gone from wetlands to wings, how we've made this transition beginning in 1943. And again, I point out this rail line across Jamaica Bay, which is the current day part of the New York City subway system. This is, as you could see, a useful reference point that spans the construction period of Kennedy Airport. Well, here again is the 1891 U.S. Geological Survey topo map. And what's interesting is that when it was updated only 7 years later, there was evidence of some human development here at Idlewild Point, specifically a hotel and resort. And again, I've shown you the outline of the airport property in the central terminal area so you could see how it relates to this development. And you can see that there was some evidence of some roads and some buildings beginning to encroach on this area that eventually became Kennedy Airport. I was able to find an older map going back to 1873 that made mention of a clubhouse. No further details of what it was. Clearly something that could only be accessed by boat. There were no roads into this area at the time. But it does indicate that humans had some sort of development in what eventually became Kennedy Airport, going back perhaps 150 years or more. And it's understandable why this occurred, because at that time, Jamaica Bay was quite rural and was considered a recreational area for the inhabitants of New York City and surrounding areas. I'll put a date on this aerial photograph in a minute, but this is the oldest aerial photograph I've found, and I'm focusing here on Idlewild or Long Neck Point because we know from material found online that this was the site of what was called the Idlewild Hotel circa 1900. And as part of this hotel development was this tower that was built in the end of the 19th century that I noted at the beginning of my presentation. And this was a combination lighthouse, observatory, and a water storage tank house. And by the way, you'll notice from this sketch that the tower and surrounding dock and other facilities supported on timber piles. And that's very important because those timber piles are still buried beneath the ground here. We know from descriptions of the Idlewild Hotel online that when they constructed the facilities here, they built hard shorelines of riprap, large pieces of stone, that there were numerous structures throughout this area supported on timber piles. And by the way, this aerial photograph was clearly taken during low tide. You can see that the natural channels are the dark, almost black areas. And here we see Long Neck Creek kind of curving through the area. These lighter gray areas, these are mudflats, if you will, areas that are exposed only at low tide. Very typical geomorphology that you see in marine wetlands to the present time. Well, we know from a U.S. Geological Survey publication that as part of the Idlewild Hotel that they installed a 2-inch 50 millimeter diameter well down about 200 feet, 60 meters, and at the time it was fresh flowing artesian water, and this was what was used to supply the development of the Idlewild Hotel and environments. We understand now that this well would have been screened within the Geotechnical gravel, which, as I indicated earlier, was at the time fresh flowing and artesian, but now is brackish due to subsequent over withdrawal. There are a number of newspaper articles that one can find online. This one from the early 1920s talks about a proposed 2,000 bungalow development of this Idlewild Point area. Apparently there were grand plans to make this into a resort colony. However, these plans were stopped by the fact that Jamaica Bay, which had been a recreational area, as I noted, became contaminated by human waste from sewage. There was basically no sewage treatment at the time. So it appears that there was probably not a lot more development in this area at the time, but when this aerial photograph was made in 1924, we could see there were some structures. We could see from the shadows, fairly major structure here. This might have been the Idlewild Hotel, perhaps another structure here. We know that this structure here was a coal silo. We know from material online that they would bring in anthracite and bituminous coal by barge, store it in the silo, and then distribute it through the region. For the first half of the 20th century, coal was a major fuel for both homes and businesses throughout the New York area. And also point out clearly there was some road development that went along with this. You can see some additional structures around here. So the point I'm getting at is there was some modest human development. And as I said, all of the hundreds, if not thousands, of timber piles that were driven to support these structures, these are still buried somewhere under the Kennedy Airport property. So it begs the question, where? Well, let's see if we can figure that out. This is a fairly recent aerial photograph, and on it I've noted the 8 current and recent terminal locations. As we know, in recent years, we number the terminals at Kennedy Airport. Before that, for its existence, these terminals used to have names. For example, Terminal 4 used to be what was called the International Arrivals Building. And that was the primary passenger terminal at Kennedy Airport for decades until it was replaced by Terminal 4. For reference purposes, this is where the original 1948 terminals, I'll show you a photograph of them shortly. This is where those terminals were located in the current Terminal 5, 6, and 7 area. Well, if we scroll back through time to 1924, this is now an enlarged view of that 1924 aerial photo. I previously just showed you Idlewild Point. We can see where this Idlewild Point development was in relationship to the terminal area. Note the roadways going through here. Again, all of this was buried when they constructed Kennedy Airport. And if we scroll back to more or less the present, we could see that fortunately where most of this development of the site was just misses where terminals 1 and 2 were constructed. Most of this development with the piles and the riprap now buried in the fill is underneath runway 13R31 left. But certainly some of this early development is something that all the stakeholders involved in this proposed reconstruction of Kennedy Airport, I would think, want to keep in mind. Because the airport property, the point I'm getting at is the airport property was not quite as pristine as a lot of people like to think at the time the airport was built. There were areas of development, and this was not the only one. Because in addition to the Idlewild Hotel, there was a golf club that was built, unfortunately, right around the time the Great Depression started, 1930. And as you can see, this golf club covers a good part of the present-day terminal area. And the important part of that is that there was fill placement, road construction, building construction as part of that. And again, all of this old construction, all this old infrastructure is simply buried under the fill at Kennedy Airport. So the bottom line is, any structures that require deep foundations, there is a possibility, depending on where you are within the airport footprint, of encountering obstructions from this old historic construction. I think we should take this in mind more than we have done in the past. But for the most part, other than that development, this is what the site looked like at the time it was built in the 1940s. You had classic marine tidal wetlands, tidal sloughs. There were some shacks, buildings, if you will, probably for fishing. Some infrastructure development in the form of electricity throughout the area. Because the airport was built during the World War II, there's not an abundance of aerial photos showing the construction, but we can get an idea of what the construction was like by looking at the construction of Cross Bay Boulevard in the 1920s. Cross Bay Boulevard is a major thoroughfare across Jamaica Bay, and it was built on landfill created by hydraulic dredging. So essentially, a hydraulic dredge is placed out here in Jamaica Bay and excavates the upper glacial aquifer, which is a medium to fine sand, pumps a slurry of sand and water, and then deposits that slurry. The water drains off and leaves the sand particles behind, and you see this light-colored material is all the medium to fine sand that is the remnant of this hydraulic dredging. To orient ourselves a bit, this is the rail line that goes across Jamaica Bay. Here's the Broad Channel station that exists at the present on the subway system. Here's Aqueduct Racetrack, and Kennedy Airport pretty much goes from around the subway line, Aqueduct Racetrack, all the way around here, curves around, and outside the limits of the photo. So again, this part of Jamaica Bay, all of these wetlands areas, this was all covered by hydraulic filling, as you see being done here about 20 years earlier. Prior to hydraulic filling, there were some settlement plates that were placed. This is a very typical settlement plate used in the New York City area in the 20th century. You have a steel plate with a steel pipe placed in the ground. Surveyors take elevations at the top of the pipe. The hydraulic fill is then placed, and extensions are placed on this pipe as necessary for continued readings. The thickness of the hydraulic sand fill that was placed at Kennedy is, in round numbers, about 15 feet is a typical average. So 4 to 5 meters in thickness is a good average. If you're interested, there's a nice little paper that was written. You can find it online that talks about some of the early measurements of settlements and things like that. This is an aerial photo of Kennedy Airport taken just prior to opening for service in 1948. Here you see again Cross Bay Boulevard that we saw being constructed in the 1920s. This is now about 25 years later. Here we see the rail line across Jamaica Bay. This is the location of the original terminal buildings. Again, today's terminals 5, 6, and 7. And the press at the time called this Jamaica Bay Sahara. Apparently they had a problem with blowing sand from the hydraulic fill. This is a not uncommon problem we've had with other hydraulic fills in the New York area in the second half of the 20th century. One of the interesting things is the original airport design called for 4 pairs of parallel runways that you can see highlighted here. And the interesting thing is that some of these runways are still in existence as runways. Others have been repurposed as taxiways. Others have disappeared completely in the current day configuration of the airport. And again, here's the original terminal area here. So here's an aerial view of the terminals as they existed in 1948 when the airport opened for commercial service. You see the original short control tower here. This is a very typical subsurface profile through certainly the central terminal area of Kennedy Airport. We have the hydraulic sand fill that was placed, again, about 15 meters, perhaps about 15 feet, 4 meters. Stratum of the marine tidal marsh, organic clay and peat. The upper glacial aquifer that we now know is the Belmore Formation, which is sand. The Wanto Formation, which where present is an organic clay. And the Merrick Formation, which is also coarse grained soil. And had this continued a bit deeper, we would have encountered the Gardener's clay. Well, these are classical, what we call friction or floating pile conditions. And the state of practice in the New York City area in the 1940s when the airport was built was the use of timber piles. So this was the deep foundation of choice when the airport was built and for several decades thereafter. So foundation selection was pretty static in terms of using timber piles driven not a very deep distance, as we'll see, into the upper glacial aquifer, the Belmore Formation, until about the early 1970s, when geotechnical engineers started to look more closely at changing the foundation design for the first time. So this brings us to the next segment of my presentation I call Foundation Engineering Milestones. And what I'd like to do in this segment is to highlight the geotechnical and predominantly foundation engineering milestones that were encountered or developed at Kennedy Airport. And while they were unique to Kennedy Airport, we'll see that they do have a much more global applicability. But for now, I'm just going to talk about things that were very specific to Kennedy Airport. It's useful to put ourselves in the mindset of where deep foundation engineering was at the time the airport was began construction in 1943. And this is by none other than Carl Terzaghi himself. Basically said that the state of practice, the state of knowledge, the state of art at the time, if you were designing a deep foundation, is that you couldn't do any calculation to say what the capacity or resistance of that foundation might be. The only thing you could do was to rely on local experience, what worked, what didn't work, or to perform a field test, what we nowadays would call a static load test, to failure. So it's very interesting to see how crude the state of the art was at the time that the airport was being designed and built. Basically, the philosophy was there was no way to design a deep foundation. You just go out there, bang some piles in the ground, and hope for the best. Again, this is a very typical subsurface profile in terms of SPTN values and normalized tip resistance of a cone penetrometer throughout the central terminal area of Kennedy Airport. And the timber piles that were used for the first few decades were, as I said, found at very shallow depth within the upper glacial aquifer. Typically, the piles were only embedded about 10 feet, 3 meters into the Pleistocene sand, the Belmore Formation. And here you see a typical creosoted timber pile in the fixed leads of a pile driving rig. One of the things you often see on pile driving rigs in the New York City area is a power auger attached temporarily to the side of the leads. And this is because very often in the fill, now at Kennedy Airport the fill is hydraulic sand, so in general does not have obstructions. But in many areas the fill is non-soil material that has simply been dumped there, construction debris, things like that. So very often there's a need to auger through that fill material before you place the pile in the ground and start pile driving. So you'll see this power auger on a number of other pile driving rigs in subsequent slides. By the early 1970s, which is when my firsthand experience at Kennedy Airport began, the so-called 30-ton timber pile was really the state of practice at Kennedy Airport. And this is a pile that has a 60 kip or 270 kilonewton service load. I emphasize that these are service loads. So we would be looking at ultimate or failure or ULS loads of about twice this. Now the interesting thing is that the state of practice in the New York City Building Code at the time is that piles of this capacity, you did not have to do any analysis. You did not have to do any static load testing. You simply applied the so-called Wellington or engineering news formula. So what that meant is if you wanted a certain capacity pile, if you knew the rated energy of your pile driving hammer, the professional engineer in the field who was monitoring the pile driving, they would simply count the number of blows per foot of pile driving, and when you reached a magic number per the engineering news Wellington formula, then pile driving would stop. Well, one of the things that troubled Port Authority engineers, and again I can say this firsthand because I was working as a geotechnical engineer for the Port Authority at the time, in the early 70s, is that if you used a single acting hammer versus a double acting hammer, you would get very different pile lengths. So what we're saying here is that if you went out to Kennedy Airport and you had a timber pile and you wanted the same load-bearing capacity from that pile, whether you used a single acting steam air hammer or double acting steam air hammer, you would wind up with piles of very different lengths. So the same number of blows with these two different hammers would give you piles of different lengths. Well, the question is why? Obviously, this is very troubling. And in the early 1970s, 1972 to 1973 to be exact, there was a test pile program. And at that time, it was proposed to build a parking garage for this International Arrivals building, where today's terminal number 4 is located, and also a rail terminal. Believe it or not, back 50 years ago, they were talking about extending the Long Island Railroad from Penn Station in Manhattan to Kennedy Airport to give passengers a one-seat ride to the airport. Unfortunately, that rail line was never built, nor was the parking garage, but the test pile program was performed anyway. And it was a rather comprehensive program. It looked at existing types of piles, old technology in terms of piles that was on its way out in terms of economic viability, and for several things that were new and radical at the time. Looked at increasing the allowable load on timber pile to 80 kips from 60. Looked at a variety of steel shell or pipe piles that were concrete filled after installation. This was the Covey pile, which is a constant diameter thin wall shell driven with an expandable mandrel. Monotube pile, which is a partially or semi-tapered pile that has the very distinctive vertical fluting on it. And the Raymond step taper pile, which is another thin wall shell pile driven with a solid mandrel. And again, you'll see here the ubiquitous power auger on the side of the fixed leads of the pile driving rig. There was some thought to pushing the envelope of technology and using bulb piles with a relatively high load-bearing capacity. One was the Frankie pile, what we nowadays know generically as a pressure-injected footing. And the other was a then new invention in the New York City area called the tapered pile tip, or TPT pile. And the TPT pile was just a precast concrete, this is normally reinforced, not pre-stressed, precast concrete plug, if you will, with a constant diameter extension, in this case a thin wall steel shell. And then this entire assembly is driven into the ground and the shell is filled with fluid concrete at the end of driving. Of course, they did look at the difference between single and double acting hammers. There were some very high precision static pile load tests using electronic load cells and special optical survey. First time at Kennedy Airport, and quite probably the entire New York City area, that on-pile dynamic measurements were made. Things we do every day now were quite revolutionary 50 years ago. This was the use of the case method, what we nowadays call the PDA, pile driving analyzer, and the CAPWAP office analyses. Also the use of the wave equation, in this case the Texas Transportation Institute version. Again, nowadays used all the time, but then at that time we still had mainframe computers and punch card input, so this was quite revolutionary. The single biggest outcomes from this in terms of foundations was the realization that rated energy of a pile driving hammer is a number that you never see in the real world. All pile driving hammers have an efficiency that is somewhat less than 1 or 100%. And we now understood why there was such a disparity between the single and double acting hammer, and that's because the single acting hammer had an 80% or better efficiency, whereas the double acting hammer was miserable and only had about a 30% efficiency. So even though both hammers had the same rated energy, the actual energy getting to the head of the pile was drastically different. Also, the realization that the Engineering News or Wellington formula was inaccurate. It simply did not compare well to the results from static load tests. Well, in reality, that was really nothing new. If you look at the published record, engineers knew as far back as the 1930s that the so-called pile driving formulas that some people still like to use really gave incorrect results. So this just puts some numbers on just how wrong these formulas can be. Well, about 15 years later, in the late 1980s, there was another test pile program. This was for a proposed rebuilding called JFK 2000. The radical difference here was this was for the first time that we realized we had a design for seismic loading and the potential for seismic liquefaction. So really the late 1980s is when we had the realization that earthquakes were certainly likely in the East Coast of the United States in general and New York City area in particular, and we had to design for them in terms of foundations. And these changes have remained to the present time. Well, the problem was, again, here was the typical timber pile, only embedded about 10 feet, 3 meters in the upper glacial aquifer, the Belmore Formation. Unfortunately, this was precisely the part of the UGA that was expected to liquefy in an earthquake. And obviously, that's not very good when the bearing stratum of your pile liquefies. Late 1980s was the first use of the cone penetrometer at Kennedy Airport, and this was just a basic cone that measured tip resistance and sleeve friction. I looked at a diversity of piles, including some unusually large diameter piles, 26-inch diameter, 660 millimeter diameter piles. These are very unusual even at the present time for terrestrial piles in the New York City area. Some of these piles were driven as deep as 100 feet, 30 meters below the ground surface. Very quickly, the design engineers of the Port Authority settled on monotube type J piles, which is the intermediate taper with an embedment of about 60 feet or 18 meters. And this type of embedment, 60 feet, 18 meters below ground surface, this is still fairly common at Kennedy Airport to the present. Although, as we'll see, the type of pile used has changed a bit. This type of embedment is still pretty common. There were some instrumented static load tests, and we're going to talk a lot more about these later in the presentation because these gave us some very interesting results. One of the things we realized by the late 1980s is that when you do dynamic measurements, you need to do restrike measurements in addition to end of initial driving. So one of the revolutionary things that was learned in the late 1980s was that piles in sand will tend to gain resistance over time, or at least the first few weeks and months after installation. And we understand this now, but then it was revolutionary because the thinking at the time was, when you drove a pile in a clay, it would gain strength, the soil would gain strength over time as it consolidated, so the pile would gain resistance. But it was assumed that when you drove a pile in sand, the resistance was the same the day you drove it as a year from now. So this was a real paradigm shift. There was also modest testing of drilled shafts or bored piles, but at that time these were a novelty in the New York City area. Of course, they are not at the present. But the drilled shafts really never caught on at Kennedy Airport, even to the present. Well, there are quite a few lasting outcomes from this late 1980s test pile program. Certainly the need to install deeper piles for seismic liquefaction, and this remains to the present. The consideration of lateral loads. Tapered piles remain the deep foundation of choice, but instead of timber piles, we use a steel pipe pile that is concreted after installation. The recognition that we get this gain in pile resistance, what some people call setup or soil freeze, with time after driving. Again, we recognize this now and we routinely do restrike measurements. The static load test on the instrumented taper piles indicated some things that a lot of people don't know. Most of these things people know. Some of these things most people don't know. First of all, the gain in resistance in piles in coarse grain soils appears related to stiffness, not to strength. And I emphasized stiffness because this will be a theme in the rest of my presentation, that one of the real changes in deep foundations that we're looking at in the present and into the future is to focus more on stiffness of the ground and not just the strength. Because stiffness is really the key to understanding a lot of behavior with deep foundations. And also significant residual loads. And in the cases we'll see, as much as 100% of the tow resistance was mobilized and locked in as the result of driving. And again, residual loads are something that I'm going to emphasize in the remainder of my presentation. They're something we've known about since at least the 1950s. We've tended to forget about them in recent decades. We need to remember them better in the present. Well, if we now move on to about 2000, this is when they built the present air train system as well as some new terminals at Kennedy Airport. And the real shift at that time was, up until 2000, most of the changes in foundations at Kennedy Airport had been the result of the Port Authority engineers looking to change things. But in 2000, it really was the contractors pushing the envelope of change. What happened by 2000 is that steel piles at Kennedy Airport were being pushed to the limit. People were looking for larger and larger allowable loads. Again, these are service loads that we're talking about. And this meant the use of monotube type Y piles, which have the maximum taper available in the monotube pile line. This is also when the taper tube pile was developed. What was learned around 2000 is that the monotube pile, because it is made out of cold form steel, the thickness of the pile wall can only be certain maximum. So really they'd maxed out on the design capability of the monotube pile. The taper tube pile is a semi-tapered or partially tapered pile, but it's made out of hot rolled steel sheet, so it can have a much thicker wall. Here you see the taper tube piles. It has a constant diameter upper section, a tapered lower section, and yes, once again, you'll notice the ubiquitous power auger on the side of the fixed leads, the pile driving rig, very typical in the New York City area and elsewhere. Again, the constant diameter section, the tapered section, and they're connected with a factory weld, and there's a closed toe as well. So this is driven in the ground and then filled with fluid concrete afterward. Another change that occurred on the cusp of the 21st century was the switch from seamless pipe to spiral weld pipe. And spiral weld pipe had not been allowed for pipe piles for a very long time. And the reason is that the quality of spiral weld pipe was not that good, and sometimes the piles would literally tear apart during driving. But by 2000 or so, the quality had improved significantly. And spiral weld pipe is simply a much more economical alternative than seamless in this application. But really the most notable outcome from this work around 2000 was the commercial emergence of the taper tube pile, which really dominates the tapered pile market in the United States at the present time. And there were some static load tests that went up to 1,000 kips, 4,500 kilonewtons ULS, or failure load, and that was more than 8 times that of timber piles at the time. This 1,000 kips has since been exceeded, but certainly at the time this was quite dramatic results. The next segment of my presentation is titled Insights Gained and Lessons Learned. And what I'm going to do here is that I'm going to take the specific issues that we've learned at Kennedy Airport, or things we've learned from at Kennedy Airport, and show you that they're not unique to the airport and that they really have a broad global relevance to geotechnical and foundation engineering. So I want to take what I talked about in the preceding segment and try now to extend it to things that should be of issue to foundation engineers around the world. And I'm breaking this segment up into several topics, cover everything from site characterization, resistance calculation, and construction quality assurance. Well, let's start off with some basic definitions. First and foremost, I use the word pile to mean a driven pile. I realize that in much of the world outside the United States, the word pile is synonymous with a deep foundation. So you need to say driven pile, bored pile, jacked pile. Here in the United States, when we say the word pile, it implies a driven pile. And I'm going to use that terminology. It's simply easier and gets the job done. Also, in terms of terminology, I use basically terminology that Fellini has proposed about 20 years ago. I've made a few modifications to this. I use the terms head and toe for the two ends of a pile, or the ends of the shaft. When I use the word resistance, I'm talking about the support that the ground provides to a pile, whether along the shaft or at the toe. When I use the word capacity, that relates to the loads that are applied at the head above the ground surface. Taper piles figure very prominently at Kennedy Airport and in the remaining presentation. So we need to define taper, and I use the quantity of taper angle. There's about 10 different ways to define taper, and I do want to point out to you, you should always be very careful when you read any sort of document about tapered piles or tapered deep foundations in general, because there's probably 10 ways to define taper. Not all authors use the same definition, and most authors do not explain or define how they define taper. So you have to be careful about that. I like this angular definition. Taper really applies to all types of deep foundations very easily. And you could see typical taper angles. Timber piles only about 0.2 to 0.3 degrees of angle. And steel piles, maximum about 1 degree of angle. Because precast concrete taper piles vary with the region or country they're made in, you're going to see more variation in taper angle. And by the way, here in the United States, we use a decimal point in the way that much of the world uses a comma. So that's another definition I do want to point out. Let's move on now to site characterization. As I mentioned earlier, the basic cone penetrometer that measures tip resistance and sleeve friction was first used at Kennedy Airport in the late 1980s. And of course, we get these profiles that we're familiar with. The piezo cone with the pore pressure sensor in the collar or U2 position, that's most common nowadays. This was introduced at Kennedy Airport in the 90s, and of course this gives you the additional parameter of a pore pressure profile. More recently, the seismic piezo cone has become in common use at Kennedy Airport, and from this you get shear wave velocity measurements. Now, with the tip resistance, sleeve friction, pore pressure, typically you'll get these about every 20 to 50 millimeters. That's every 1 to 2 inches, depending on the diameter of the cone that you use. The shear wave velocity is obtained typically about every meter, every 3 feet. And I'm going to be emphasizing the seismic piezo cone. I think people are aware of it, but they think of it more as a research tool, but really it is an everyday tool that should be in the everyday mainstream use in foundation engineering. And hopefully I'll show you why. Although there are many in situ testing devices, in my mind, in foundation engineering, the cone penetrometer should always be the device of first choice. For the simple reason is no other in situ device has so many correlations, literally dozens of empirical correlations for soil properties and parameters with the data that you measure in a cone penetrometer, especially a piezo cone and even more so the seismic piezo cone. This is especially noteworthy for coarse-grained soils, as dominates Kennedy Airport and many other areas, because as we know, these soils are pretty much impossible to test in an undisturbed manner in traditional laboratory testing. And again, the piezo cone with the shear wave velocity measurements adds a particular element that has not been present previously. The main area where the seismic piezo cone is useful is giving us an idea about soil stiffness. And again, I highlighted stiffness in the preceding segment, and I will do that for the remainder of this presentation, simply because I hope to show you that soil stiffness really is terribly important with deep foundations. With deep foundations, we tend to obsess on soil strength and failure. We really need to be thinking more in terms of stiffness and settlement. And the seismic piezo cone really gives us data that no other device gives us, especially for assessing what I call the microstructure, the aging or cementation. I'll just look at a couple of parameters that we can get from the piezo cone and seismic piezo cone. As I said, there are dozens, and we could spend hours just talking about that one topic. When we talk about coarse-grained soils in terms of soil consistency, we tend to think in terms of relative density, something that's impossible to measure in the laboratory in an undisturbed sample of coarse-grained soil. We can use empirical correlations to get profiles of relative density, as you could see here, with data points maybe every 1 to 2 inches, every 20 to 50 millimeters. Actually, when it comes to coarse-grained soil consistency, nowadays we prefer to talk about the state parameter psi, and this comes from critical state soil mechanics. The reason is that the state parameter gives us a single number that divides between the contractive and dilative behavior of a sand. Contractive, of course, means volume decrease when we shear it. Dilative means volume increase. And this is very critical for a lot of soil behavior, especially seismic liquefaction. So the state parameter gives us much clearer insight, as you can see from this blue dividing line I've shown you here, that we don't get with relative density. So this is a very typical interpretation at Kennedy Airport. Here we see a very distinct contractive zone here, correlates with low relative density, and no surprise, this is exactly the part of the upper glacial aquifer that we expect to liquefy in an earthquake. Another contractive zone down here, again, correlates with low relative density down here at about 16, 17 meters, about 50 some odd feet. Stress state. The brown line shows the calculated vertical effect of overburden stress. Again, the yield stress, or some still prefer to call it maximum past effective stress, a parameter that is essentially impossible to measure in a lab for a sand. We can get estimates of this from the cone penetrometer. The yield stress ratio, what we used to call the overconsolidation ratio, again, we could get estimates of that. And a parameter called the overconsolidation difference, which is simply the numerical difference between yield stress and overburden stress. This gives us an idea of the distribution of overload or pre-stress in a soil deposit. However, for stress state, the most important parameter, I think, for deep foundations is K sub O, coefficient of lateral earth pressure at rest. For reasons that I will explain in detail in the rest of my presentation, this is shaping up to be one of the most important soil properties for all types of deep foundations, not just for piles, and certainly not just at Kennedy Airport or piles and sand. And that's because state-of-art methodologies have shown that anytime you're looking to assess the axial resistance in either compression or uplift for a deep foundation, K sub O plays a role. And that's because K sub O governs both the shaft resistance, okay, the horizontal effective stress is equal to KH times the vertical overburden stress. I like to use the KH-KO ratio. KH is simply the horizontal earth pressure coefficient after you install a deep foundation. K sub O is that coefficient before you install it. So the KH-KO ratio really reflects how you change the horizontal stress state when you install a pile or a drilled shaft or a jack pile or whatever into the ground. And you're going to see these two parameters I've highlighted in red throughout the remainder of this presentation. I'm also going to show you that, believe it or not, the horizontal stress in the ground controls toe resistance. We're used to thinking about vertical effective overburden stresses governing toe resistance. In reality, it's the horizontal stresses that govern toe resistance. Ground stiffness or modulus. Again, this is really where the seismic piezo cone gives us invaluable information. We can get a depth-wise profile of shear wave velocities, and then simply using the theoretical relationship between shear wave velocity and shear modulus, get a profile of G sub O, which is the small strain shear modulus. Most of the world calls this parameter G sub O. Here in the United States, we tend to call it G max. They're the same thing. And whether you call it G sub O or G max, this is, again, you'll see this in the remainder of my presentation, this has emerged as being an essential soil property for forecasting. And by the way, I like to use the word forecast as opposed to predict. For forecasting the resistance of all types of deep foundations in both compression and uplift. And again, in my mind, the seismic piezo cone is the tool of choice for measuring shear wave velocity. As I indicated earlier, one of the things that we could use the seismic piezo cone for is to give us some advanced insight into a soil's microstructure that is related to aging and cementation. And the reason this is important is one of the things that has emerged in recent years, primarily with regard to seismic liquefaction, but now also with deep foundations, is the difference between the behavioral age of a soil and its geological age. Now, just like a person only has one age, a soil deposit only has one geological age. It's when nature created that soil deposit in the ground or humans placed that soil in the ground. However, that soil can have different behavioral ages because the behavioral age can be what we call reset. The point being is you could have a soil that is 100,000 years old geologically, but behaves as if nature just placed it yesterday. And that's because there are various natural things, such as earthquakes, as well as human activity, that can reset the behavioral age of a soil. And the reason for making this distinction is we now realize that behavioral age is very important for both seismic liquefaction potential as well as deep foundation performance. And really only a seismic PISA cone could give you insight. And you see here, what I'm showing you here is for Kennedy Airport, very typical profile, where we're looking at ASF as just an age scaling factor. It's an empirical factor to give you an idea of the age of the soil. We see these soils up here behave very young, Holocene, like very young soil. But then as we get deeper in the ground, notice how the behavioral age increases through the Pleistocene heading towards the Tertiary. Next topic is material issues. We've certainly known for a long time that both wood and Portland cement concrete can be damaged during pile installation, either by handling or driving. We know that when we drive a pile, we generate both compression and tensile stresses within the pile shaft. Generally, we don't worry about damage to steel, simply because steel is stronger than either wood or concrete, and also has the same strength and compression and tension. But towards the end of the 20th century and up to the present, we really pushed the envelope when it came to steel pile technology. So we really were, in terms of trying to get more and more geotechnical resistance out of these piles, we were pushing the structural resistance to its limits. And as I indicated previously, this is when we began to realize that the monotube pile had maxed out structurally. Because it's made of cold form steel, you can only make the wall of the pipe so thick, and there were problems getting monotube piles in the ground without physically damaging them. And this is what led to the development of the taper tube pile, where because it's made out of hot rolled steel sheet, we don't have these thickness limitations. And that's what has allowed us with the taper tube pile to continue to push the envelope over the last 20 years with ever larger, higher geotechnical resistances. I also mentioned previously the transition to spiral welded steel pipe as the quality of that pipe improved. However, because we keep pushing the envelope and pushing the limits of steel, we need to be careful. One of the things we learned at Kennedy Airport, we have to be careful between aligning the pile with the pile head. And I'll give you an example of what I'm talking about. Okay, this is a piece of constant diameter steel pipe. It's the upper portion of a taper tube pile. It was cut from a taper tube pile driven at Kennedy Airport in 2012. What happened here is that the pile was not properly aligned with the hammer in the pile driving leads. So this was a pile driving error. This was not a taper tube pile problem. It was a pile driving problem. And it shows you that because of the misalignment, even though this is high yield steel, the very classical pattern, this is what happens when you yield or fail the head of a steel pipe pile. You get this accordion shape look to the head of the pile. But actually the more interesting thing of this photo are these welds. These are the factory welds in creating welded seam welded pipe as opposed to seamless pipe. And the interesting thing here, and the reason I'm showing you this picture, is that even though the steel yielded, this weld did not fail. So the factory weld, when they made this piece of pipe, is an ideal weld. As we know, when we weld metal, an ideal weld should always be stronger than the parent metal on either side. And this photo simply shows that even though the steel yielded, this weld did not fail. So that was a very good quality weld. If you want to learn more about making steel pipe for piles, I suggest you look up this nice article that was published in Pile Driver magazine of PDCA, the Pile Driving Contractors Association here in the United States. Okay, I want to talk now about installation issues. And here I'm going to focus on residual loads, which I briefly touched on in the preceding segment. Residual loads are simply the compressive forces that develop naturally within a pile shaft. And they're really due to the fact that when you drive a pile in the ground, it's kind of a 2 steps forward, 1 step backward behavior. You know, when you look at a pile being driven, it looks like the pile is continuously moving in the ground, and it is. But because it's all happening in a millisecond time frame, you don't see that it's really a 2 step forward, 1 step back sort of process. And this is what I mean. If we look at an arbitrary fixed plane somewhere within the ground, every time you impact this imaginary pile, it goes down, but then it rebounds slightly. Goes down, rebounds slightly. So again, 2 steps forward, 1 step back with each blow of the hammer. This is seen more formally on this graph. These are high precision measurements of what's happening during pile driving. Essentially what we see is things are steady just before the pile is impacted. The hammer hits the pile goes into the ground, but then immediately begins to rebound, oscillates around, settles down until it's impacted again. Actually, it's more insightful if I simply inverted that graph, because then it looks like what's actually happening in to the pile. So here we are, we impact the pile goes into the ground, and in this case about 31 millimeters, right? So a bit more than an inch. The pile goes into the ground, but then the pile rebounds, all right? So here the pile is moving downward relative to the soil, but then here the pile is moving upward relative to the adjacent soil, oscillates around, reaches an equilibrium until the next hammer impact, and the process is repeated. Well, the net difference in penetration between where we started and at the end of the hammer blow, this is what we call the final set of the pile. So yes, there is a continual migration or settlement to the pile in the ground during driving, but it is a very complicated 2 steps forward, 1 step backward sort of arrangement. Well, because of this complex behavior where the pile first moves down relative to the soil and then upward, what happens is we produce drag loads on the soil around the pile shaft. Now, some people call this negative shaft friction or negative skin friction. In the terminology that I showed you earlier, these are what are called drag loads. Now, conceptually, these are similar to the drag loads that we get from down drag. I suspect most people are more familiar with down drag than they are with residual loads. Down drag is when you place any type of deep foundation in the ground, but then the ground settles. Usually it's due to a stress placed on the ground, and you have consolidation of the soil, so the soil settles, and the soil moves downward relative to the deep foundation and creates a drag load that we call down drag. So down drag is soil settling relative to the more or less stationary pile in the ground. On the other hand, the residual loads we're talking about is when you have a drag load, where the drag load that produces these residual loads is the result of the pile moving upward relative to the more or less stationary soil. So the cause effect is different between residual loads and down drag, but the result is the same. We get a drag load in the upper portion of the pile shaft. Well, these residual loads increase with depth. They're often largest just above the toe, and importantly, they are non-zero at the toe. And here's the definitions I showed you previously. Here's the drag load. Again, what a lot of people call negative shaft friction or negative skin friction, as opposed to resistance, which is a positive shaft friction or skin friction. So we're saying what residual loads are is even though after installing the pile in the ground and the load at the head of the pile is 0, within the pile shaft there is a non-zero compressive force and also a load at the toe. Now, of course, this pile has to be in vertical force equilibrium, so the drag load in the upper portion of the shaft has to be balanced by resistance in the lower portion with some transition in between, and then there is a toe resistance. So all of these vertical forces have to be in a vertical force equilibrium because there's no applied load. Now, where this transition occurs between the drag load and the resistance, we call this the neutral plane. And this will be a term that will come up time and time again in the remainder of my presentation. Well, I'm emphasizing these residual loads both here and in the remainder of my presentation for a very good reason. And that's because, as we'll see, they are tremendously important. And as we'll see, they're important not just with piles that are driven into the ground, but they turn out to be important with pretty much any type of deep foundation. It may surprise you. The point I will be getting at is that we need to pay much more attention to residual loads than we do at the present time. Well, for now, let's just say, unless corrected for, the residual loads give us an incorrect perception of what the shaft loads and toe resistance look like. Now, we've known about residual loads since at least the 1950s. There's a paper by Manzer and Kaufman where they talk about residual loads. There was some academic research into residual loads in the 1980s, but for the most part, it seems residual loads seem to have fallen below everybody's radar, both in practice and academic research. And I think part of the reason is that they were thought to be kind of a geotechnical curiosity that disappeared when you loaded the pile and really did not cause any structural issues. But we'll see that both of these perceptions are quite incorrect. And the real eye-opener in this regard was the instrumented static load test we did at Kennedy Airport in the 1990s on some monotube piles. And they revealed that residual loads were quite significant and a very important consideration. What we're looking at here are some interpreted results from some instrumented static load tests on monotube piles in the 1990s. There were two piles, pile 2, pile 3. What's interesting is that pile 2 hit an obstruction at a depth of about 4 meters, 13 feet below the surface, which is the old ground surface, and specifically it was a piece of Portland cement concrete. If you think about what we talked earlier, that's not surprising. I don't know the exact location of these two test piles. It was somewhere within the central terminal area here. But given the fact that we know that there was development associated with the Idlewild Beach Golf Club, there were roads leading to and from Idlewild Hotel, that a pile would hit a concrete obstruction is no surprise. And again, something that all the stakeholders involved in the future redevelopment at Kennedy Airport should keep in mind. There's very good likelihood of hitting obstructions at certain parts within the certain central terminal area. Anyway, so we're just going to look at pile number 3, and at its maximum load of 2,500 kilonewtons, about 560 kips. And the pile was just on the cusp of the geotechnical ULS, the ultimate limit state or failure at that point. Now, the measured load, as I said, these instrumented tests shown by the dashed blue curve, indicated that there was no tip resistance, which was kind of surprising. But we can understand why they reached this incorrect conclusion. The instrumentation was placed inside the steel pipe of the monotube pile after it was driven and prior to concreting, because the instruments were based on measuring the strain in the solidified or hardened concrete. Now, because of this, all the residual loads that had occurred during driving were missed, because those loads existed prior to concreting the pile. So that missed the residual loads that were locked in to the pile, which are quite significant, as you could see from the dotted blue curve, and more importantly indicated that these piles had a rather significant tip resistance. In fact, about 20% of the applied load was being carried by the tip, which is somewhat surprising perhaps, given that the tip diameter is only about 8 inches, about 200 millimeters on the monotube pile. And also note that the residual tip resistance was about 100% of the ultimate toe resistance for these piles. So what we're saying here, and again, notice a very classical distribution. What we're seeing here is due to drag load, the compressive force in the pile reaches a maximum, and somewhere in here is the neutral plane. So from below here we get resistance, but what we're saying is the residual loads here were so significant that it fully mobilized the toe resistance at the end of driving. So that the true load distribution in the pile looks like the red curve, about 20% due to tip resistance, 60% due to the tapered zone, and only about 20% due to the constant diameter portion of the pile here. Another significant issue related to residual loads has to do with piles such as the monotube pile or taper tube that have what I call a composite or multi-component cross-section. In this case, a steel pipe with a concrete core. Because when you have a deep foundation with multiple structural elements in the cross-section, you have to allocate the axial forces and therefore the axial normal stresses to the structural components. This is how you make sure that the structural components are adequately sized. Unfortunately, when we do this, we typically ignore residual loads. What do? We assume that, okay, I have this pile, I have this drilled shaft, I have this jack pile, whatever it is. It's installed in the ground, and I assume that all of the structural elements are initially stress-free because there's no external load on the pile or whatever type of deep foundation we have. Well, that's simply incorrect. Because of residual loads, there are some initial compressive stresses in these components. Well, let's look at the consequences of neglecting these residual loads on the structural side of things. This is just a plot for pile number 3 from that 1990s monotube test at Kennedy Airport of the residual load in the pile shaft divided by the maximum load that was applied at the end of the test. And you can see here within the taper portion is quite significant. So what I'm showing you here is that the theoretical shared load, based on the traditional assumption that all pile components are stress-free after installation but before load application, this would be the theoretical shared load. Solid blue curve. Well, however, after driving, we have this residual load in the steel component only. So what we're saying is before you even concrete the pile, no less load the pile externally, the steel pipe is carrying this load in compression. Well, if the steel pipe is already carrying this load, that means all that's left over after you concrete the pile, this dash blue curve, is the actual shared load. Quite a bit different than the theoretical load based on the stress-free assumption that's clearly incorrect. Well, let's see what the implications are about axial compressive stresses in the pile material. Let's first look at the steel pipe. The solid blue curve is the theoretical axial compressive stress in the steel pipe based on the theoretical shared load. That is, everything is stress-free initially. However, we know we have residual loads in this pile. So the green curve is the actual compressive stress after the pile is driven, before it's concreted, and before we apply an external load. Well, it's interesting to see that this lower portion of the tapered section is already overstressed just from the residual loads, before you even concrete it, before you put 1 ounce of external load on the pile. Well, this is the actual stress in the pile after concreting and applying the 2,500 kilonewton maximum load. Quite a bit different. In fact, we see there's portions of the steel pipe down here that are overstressed by 100%. And although they did not cause the steel to yield in this case, I think you could see that certainly in practice you could have a situation where you think that you have properly sized the steel pipe so it doesn't yield under maximum loading, but by neglecting residual loads, that steel could actually wind up yielding on you. Well, let's look at what's happening in the concrete core. This is the theoretical stress in the concrete. This is in KSI. This is in megapascals, based on the initial incorrect stress-free assumption that we usually make. Well, this is the actual stress in the concrete core. Notice that it goes to 0 here, which is why we interpreted the instrumented load test to say the toe was carrying no load, because the instrumentation was only based on strains in the concrete. Again, there's a difference between what we think we have stress-wise, what we actually have. In this case, we underestimate the stresses in the concrete core. That's not a surprise because we overstressed the steel pipe. So things, of course, have to balance out. And again, we see why we inferred that the toe load was 0 when in reality it's far from 0. Right? We have about 150 kips, 600 kilonewtons of toe load in this pile. Well, I want to talk now about the post-installation geotechnical resistance to externally applied loads. This is how we forecast what the axial loads are in the deep foundation after installation. One of the things we learned about clearly at Kennedy Airport is taper benefit, which is a special case of what I call compressive resistance efficiency. Taper benefit simply means, all things being equal, a tapered pile will be more efficient at load bearing in axial compression than a constant perimeter deep foundation element. And of course, pile contractors have known about this since the late 19th century. If you look at patent filings, as soon as early patents for steel and concrete alternatives to timber piles back in the late 1800s, when steel and concrete were still novel foundation materials, there's no shortage of patents for tapered piles. Because even back then, people who installed these piles for a living knew that there was a benefit to using tapered piles. One of the things we've learned in the years since then is taper benefit is optimum and maximum for piles, that is driven piles, that are in a friction or floating condition in coarse grained soil. Yes, there are times when there's no benefit to taper. If you had an end-bearing pile on hard sound rock, there's no benefit to taper. Taper benefit in fine-grained soils, well, that's still open for discussion. Some people believe there's a taper benefit. Some people believe there is not a taper benefit. My feeling is that there's not been enough in the published literature to say one way or the other. But very clearly, if you have a driven pile in a friction condition in coarse grained soil, there is always a taper benefit. You need only a very small taper angle to get this taper benefit, and that's certainly something we've learned at Kennedy Airport over the years. I created this plot recently. What I'm showing here is what I call compressive resistance efficiency, and this is on a volumetric basis. This is just, I took the maximum applied load in a static load test, divided it by the volume of the pile, and then I non-dimensionalized it to using the unit weight of water. And this is so it doesn't matter what system of units we're talking about. I'm plotting this against taper angle. So we see we have constant diameter piles, we have timber piles, monotube piles, taper tube piles. Some of them were not loaded to the geotechnical failure, the ultimate limit state, but I showed those results anyway, just to give us some additional data points. And while certainly there is scatter, one of the things we see, there is very definitely a trend that as the taper angle increases, the efficiency of the pile increases. And this is a visual demonstration of taper benefit. And we see even with a timber pile, it has a very small taper angle, only about 0.2, 0.3 degrees of angle. There's a benefit. And that's because when it comes to pile taper, a little goes a long way. So certainly one of the things we've learned at Kennedy Airport over the years is that if you have a friction pile situation in coarse grained soil, taper piles will always be more efficient. And unfortunately, although we've known this for over 100 years, I don't think that the message has gotten out nearly as much as it should. Oh, again, another thing we've learned at Kennedy, I've already touched on, is that piles, especially tapered piles, exhibit a temporal increase in axial compressive resistance after driving. That's why we do restrikes nowadays, in addition to end of initial driving. But much less well known is that this increase occurs along the tapered portion of a pile and is stiffness related. Again, I keep coming back to the stiffness issue that I emphasized early on and will emphasize further in the remaining part of my presentation. The final topic I want to touch on in this segment has to do with resistance verification, what is more formally known as construction quality assurance. Well, at Kennedy Airport, in the latter decades of the 20th century, we made some state-of-the-art advances with this. We improved the way that we did static load testing using electronic load cells and special high precision optical survey to measure pile head settlements. In 1972, for the first time, we used on-pile dynamic measurements. Of course, we take this for granted now, but 50 years ago, this was a very novel technique. Again, use of the wave equation we now take for granted was used 50 years ago at Kennedy Airport. Some of the positives, some of the good news we've learned from these experiences that really we can have a universal relevance and application. One thing we've learned, and certainly other people have as well, is that if you base your loads in a load test on jack pressure readings, you're always going to overestimate those forces by 10 to 20%. Has nothing to do with calibration of the jack. It's simply due to piston friction. Electronic load cells are more reliable and should always be used. Unfortunately, they're not. The very common dial gauges and tension wires and mirrors that we use for measuring pile head settlement will always, and I repeat, always underestimate settlement by about 10%. And that's because the supports for these dial gauges and reference wires, even though they're placed some distance away from the load tested pile, are still going to settle. So you're under measure the settlement of the head. I've seen way too many load tests performed out in the open without any sort of covering against the sun. That's not good practice. There is, as I said, high precision optical survey that you could use that's much more accurate, but it's very rare even for academic research, and that's simply a cost issue. Later on, I'll mention some ways that we might overcome this. The problem is all of these errors are additive in sign, with the net result is that your measured load settlement curve can be off quite a bit. And the reason I'm emphasizing this is that the errors are always on the unconservative side. And in civil engineering, whenever something is unconservative, it is potentially unsafe. As we know, everything we do in civil engineering is approximate. It's when the approximations give us unconservative results that we get concerned, because unconservatisms can lead to safety issues. We simply have less safety built into our system than we think. So another way of saying things is that with static load tests, the results tend to be overly optimistic in terms of how much load that foundation can actually carry, as well as the foundation system stiffness. These are two separate but related issues. And the reason I'm emphasizing this is because the static load test, past and present, is viewed as the gold standard in foundation engineering. Whether you're doing everyday production piles or conducting academic research, if you have the results from a static load test, we consider that to be the gold standard. Think about it. If you run a load test, you get a load settlement curve. We tend to think of that as being absolute incorrectness. All right? And if you compare that curve to a calculation saying how much the foundation should carry, and there's a difference, we say, oh, the calculation's wrong. That analytical method is wrong. I got a load test result. It has to be right. Your method is wrong. Well, maybe not. Maybe the calculation is correct and your load test is wrong. Even worse, in my opinion, is if you have what we call a direct analytical method. And this is where we have some empirical correlation. And perhaps the most popular one for deep foundations is the beta method. All right? This is where we say that the shaft resistance is beta times the vertical effective overburden stress. Well, how do you come up with these beta values? Well, you run an instrumented static load test. And you take those instrumented readings, you do a simple calculation, you get a beta value. Well, the problem is if your load test result is incorrect, your measurement results are incorrect, you didn't correct for residual loads, well, then your beta value is going to be wrong. And all of your forecasts that you then do based on those beta values are going to be wrong as well. I think you can see how these sorts of errors can really propagate and become very problematic. And that's why I'm emphasizing these issues now in the discussion of load tests. I think, unfortunately, in practice and research, we tend to look at the static load test as being the right answer. And the reality is it isn't. Well, let me show you a qualitative example for now. Later on, I'll show you some quantitative examples. So let's say this is a typical load settlement curve that we measure in a static load test. We use some methodology like the Davison offset method, very popular in the United States. It's wrong, but it's used all the time. Anyway, we use this method and we say, this is the failure load. This is the geotechnical ultimate limit state for the steep foundation. This is the correct answer, what you see here. And we use this, the correct answer, to compare everything else to. Well, the reality is that if you relied on jack pressure measurements, you're going to be off by at least 20%. And even if you use an electronic load cell, your settlements are going to be too small by about 10%. So the reality is this could be your actual load settlement curve. And now if you apply your failure methodology to this curve, this is the real geotechnical failure load. This is the real ultimate limit state, not this, this. And therefore, what you see is not what you get. You think that this is the load bearing of this steep foundation, and it's not, it's this. And notice this is a stiffness issue. Notice that this is a much stiffer response that you think is happening than this softer response that is actually happening. So there's two issues here. There's the difference in the interpreted failure load, and there's the difference in the interpreted foundation ground stiffness. Well, as I said, this is not just a theoretical or hypothetical exercise. This is some load tests that were run at a confidential site at Kennedy Airport, where they measured the load using the jack pressure gauge, and they measured the load using a load cell. And in this case, for two different load tests, the results were different by 25% in this case. And I would also add that, although not shown here, that these settlements are probably too small by about 10% as well. And I say that from personal experience. On more than one occasion, I've performed load tests where settlement measurements were made using dial gauges and tension wires and mirrors and all that good stuff. And we also did very high precision optical surveys that were accurate to 0.001 feet, which is about 1 order of magnitude better precision than the normal survey leveling. Well, unfortunately, we learned a lot about how to do good load tests at Kennedy Airport in the latter decades of the 20th century. But unfortunately, from what I've seen in the first 2 decades of the 21st century, we've given up some of those gains. Very interestingly, there was an article in a geotechnical magazine within the last few months where some academicians talked about laboratory testing of soil, saying that, gee, in the 20th century, we learned how to do good laboratory tests on soil. Now in the 21st century, we seem to be doing poor quality tests. And I think in both cases, the cause of this is we treat these things as a commodity. We do them on a low bid basis. Who can perform this pilot test for the lowest cost? And I've spent almost 50 years of a professional career working in private consulting. I understand that clients are always talking about costs and worried about costs. But the reality is that the difference in price or the difference in cost between a very good load test and a very poor load test is not that great. If you're going to do a load test, you're already spending a lot of your client's money just to do it poorly. You might as well spend a little bit more and really do it well. These are not a commodity. They're not a necessary evil. We should get the most out of a load test that we can. I'm not saying we have to do instrumented load tests all the time, but even uninstrumented load tests we could do a lot better in practice. What are some of these specific bad habits I've seen happen in recent years? People continue to use jack pressure and not an electronic load cell. And right off the bat, you're going to overestimate loads by 20% or more. I mean, that's a given. We've known that for decades. For some strange reason, people test piles that don't represent production piles. Specifically, if you have a steel pipe pile with a closed toe that's going to be concreted during production, you should concrete it when you load test it. Don't test the pipe without the concrete inside of it. The worst thing is what I've seen is what I call gaming the system. And what this involves is that if you don't like the load test result you get today, well, run it again tomorrow and call it a new load test. And that is simply not proper. And you see an example here. Right? This is a real world example. Here you see the first load test performed on this pile. They did not like the results, so they came back the next day and they ran another load test. And then they superimposed the two on the same plot and said these were two different tests on the same pile. The second one's better, so the pile is stiffer, the pile is stronger, everything is okay. Well, it's not okay, because when you run this second load test, you are testing a system that has been pre-stressed, it has been pre-strained. The reality is that this second load test loop, it should have been added on here. You don't start at zero. This second load attempt does not start at zero. It starts down here, because all it is a continuation of that load test the next day. And that's how it should have been plotted up and interpreted. People do this because construction specifications allow them, and I think it should not be allowed in practice. Well, this brings us to the next segment that I call current trends and directions. And what I'd like to do here is, okay, we've talked about lessons learned at Kennedy Airport. And in the preceding segment, I've tried to show you how these specific lessons learned at Kennedy Airport really can be used on a wider global basis for many types of deep foundations, not just tapered piles as we've driven at Kennedy Airport. What I like to do now is to go one step further and say a lot of these things that we've learned at Kennedy Airport that have global applicability, other people have learned as well. So what I want to do now is I want to combine the insights and lessons learned at Kennedy Airport with other knowledge that appears in the published literature and put them together. I want to curate and synergize them, and really from this to get some guidance for future trends and directions for all types of deep foundations in all types of ground conditions. So this is more of a where we would like, or I suggest we should like the foundation engineering to go on a global basis in the future. And I'm going to use the same topical breakdown that I used in the preceding segment. I think that worked out pretty well. And starting off with site characterization. To me, there's two overarching goals in both geotechnical and foundation engineering when it comes to site characterization. One is we really need to cut back on the standard penetration test and N values, or at least what we make of them. Let's realize that this is 100-year-old technology, and the standard penetration test is good for giving us soil samples to look at, but really nothing else. We should not be using methods based on SPTN values to estimate liquefaction, deep foundation resistance, footing settlement, and things like that. There are simply better ways to do things. We should be doing more to bring the laboratory to the soil in terms of in situ testing than the other way around. I don't have anything against laboratory testing, but laboratory testing is expensive, and we should use it when laboratory testing provides us with the best value for our client's money. There are many different types of invasive and non-invasive in situ testing. I've tended to focus on the cone penetrometer because certainly for the conditions at Kennedy Airport, it is the ideal in situ testing device to use, especially nowadays a combination of the piezo cone and seismic piezo cone. But there are many other devices to be used, and we should be doing more of it. As I said, in general, my opinion is that the piezo cone and seismic piezo cone should be the first choices in situ testing devices, but simply because you can do more with the data in terms of generating soil properties and parameters, especially for coarse-grained soil, than any other device. But of course, yes, there's ground conditions where the cone penetrometer does not work well. That's why we have the pressure meter. That's why we have the dilatometer. There are other devices that work in ground conditions that are not conducive to the cone penetrometer. But that having been said, your cone penetrometer should always be the first device you think about to see if it works in your conditions. Certainly, the seismic cone penetrometer, seismic piezocone gives us insight into microstructure. That's very important. And also, the piezocone, the seismic piezocone, really complement laboratory testing. As I said, I'm not against laboratory testing, especially when you have fine-grained soils that we can sample reasonably undisturbed tube samples fairly well. But the point is that the results from cone penetrometer and laboratory testing on fine-grained soils really complement each other. They provide us with synergistic results at a lower overall cost. And I'll give you an example of that in a minute. But I want to combine this with another point I want to make, and that is in situ testing is not just for big projects. I've heard this a lot, that, well, yeah, I've heard of the cone penetrometer, it's great, but I've got a small project. The piezocone, the seismic piezocone, is not just a big project device. It can be very cost effective for very small, very modest projects. So let me combine some of these. I'll give you an example that I was involved in just within the last few years. This is a site in Bergen County, New Jersey, underlain by Glacial Lake Hackensack. I'm going to talk more about glacial lakes in a bit. And this was a small project, and I'm going to show you how it was very cost effective. We did one piezocone and one seismic piezocone on this project. Well, what are glacial lakes, if you've not heard this term? Glacial lakes are simply an artifact of Pleistocene glaciation. We find them in many, many parts of the world that were directly affected by the glaciers. One of their signature features is a glaciolacustrine clay that we call a Varve clay. And here's Kennedy Airport. And we find these clays, we call them the Hudson Valley Varve clays, extend from northern New Jersey all the way up into New York State and into New England. Some of you may have heard of the Connecticut Valley Varve clays. These are actually somewhat more famous because MIT researchers studied them in the 1970s, and more recently academic researchers at the University of Massachusetts Amherst, which is actually located in the Connecticut River Valley, have studied these as well. They are somewhat different in behavior. But if we focus here on the New York City metropolitan area, again, here's Kennedy Airport, we see from these colorations that these glacial lakes, as they were called, were very prominent throughout this area. The one in particular is Glacial Lake Hackensack, and here's the site I want to talk about. As I said, this was a small project for a commercial building. There was only one each of the piezocone and seismic piezocone that was performed. And these were used very cost effectively with perhaps a half a dozen traditional borings and some very limited laboratory testing in the form of odometer tests, one-dimensional consolidation tests. This is just the pore pressure profile we see. And at this site, because it was the floodplain of the Hackensack River, we had a little bit of fill material that had been placed, a thin layer of organic clay, about 10 meters, 30 or so feet of Pleistocene sand. That's why you see hydrostatic water pressures. And from here on down, this was the Varve clay. Somewhere down around here at about elevation minus 40 meters, so almost 150 feet below the surface, we had bedrock, and this is the Triassic shale that we find throughout this area. Well, you see the Varve clay had two distinctive zones. This was a bit of a stiffer zone, and this was a softer zone. You can see the different pore pressure response. But geologists have indicated this area has very complex stress history. As I indicated earlier, we have something like 5 different glacial events have moved through this area in the Pleistocene, and each one of those events had localized advances and retreats. The stress history is very complex. When we combine that with this fact that sea level was more than 120 meters below the present level, groundwater up nowadays is here. It used to be 120 meters lower, 400 feet lower. We have a lot of desiccation of these soils. It gives us a very complex stress history. And because we take pieces of data with the cone penetrometer every 1 or 2 inches, every 20 or 50 millimeters, we get a lot more data points. What we're looking at here is the vertical stress profile. Here's the calculated overburden stress. And the red and green data points are the estimated yield stress, or maximum past effector stress, if you will, from the two pisocone and the size of pisocone soundings. And of course, a nice benefit is we get estimates of yield stress in the sand that we would never get from laboratory testing. We do 2 conventional odometer tests, consolidation tests on thin wall tube samples at the site. And here's the interpreted yield stress from those 2 samples. And we see there's very good correlation. But we also see that if all you had was these 2 laboratory test results, it would be very difficult to put together a coherent, rational picture of the stress history of this site. But when you combine these 2 results with hundreds of additional data points that we get from the cone penetrometer soundings, you can come up with a much more rational stress history profile for analysis purposes. And that's what I'm getting at, is the synergistic, complementary, cost-effective use of doing some laboratory testing, some cone penetrometer soundings, and then using these together to calibrate and verify each other to come up with a complete picture. And we could do the same thing with the yield stress ratio, what we used to call the over-consolidation ratio. Again, we see the data from the cone penetrometers, the odometer results, and again, using them together provides us with a much clearer picture of the very complex stress history of this site. I should also point out that another positive of using the cone penetrometer is we can use them for direct methods for resistance forecasting. And this is where we take the Q sub C and the F sub S, perhaps the U2 values, and allows us to estimate what the toe resistance is, what the shaft resistance is, etc. And of course, soil stiffness. I've mentioned this now several times that one of the things that as we move ahead in the future, we should be doing a lot more with soil stiffness and using the small strain shear modulus that we get as an outcome of seismic pisocones. I did mention that there certainly are soil conditions where the cone penetrometer can't be used. There are many, many other invasive and non-invasive devices for measuring shear wave velocity and therefore small strain shear modulus. So there's no excuse, no matter what type of soil, what type of rock, there's no excuse not to determine a shear wave profile and from this a small strain shear modulus. Professor Ken Stokey, as I'm sure most of you know his name, he's a leading world expert on small strain vibrations in the ground. He gave a very nice webinar 3 years ago on behalf of the ISS MGE. If you've not watched this webinar, I suggest you go to the ISSMGE website. There's no cost to view this webinar. It's a very good use of your time, in my opinion, and it will complement a lot of what I said here about, in this presentation, about the importance of shear wave velocity and small strain shear modulus in modern geotechnical and foundation engineering. Both shallow and deep foundations. Professor Stokey does talk about shallow foundations as well. I'd next like to talk about the topic of material issues. I previously talked about the potential for damaging the head of steel piles if you don't properly line up the pile with the drive system. And of course, we've known for a long time that during pile driving, very difficult conditions, that we can yield the toe of piles, H-pile, pipe pile. And this is because theory tells us that the compressive stresses at the pile toe at refusal can be twice those at the head. Less common, less well known, is that buckling can also occur during driving. Even when a pile is fully embedded in soil. The perception to the present is that piles that are fully embedded in soil, even a very soft soil, will not buckle. But that's simply not the case. It really depends on the specific conditions. And I'm going to illustrate where this can happen with a case history. So here we are, Kennedy Airport, and to talk about this case history, we need to journey to the so-called Panhandle region of Idaho. Specifically, we're on the shore of Lake Pend Oreille near Sandpoint, Idaho. Project was about 10 years ago and involved a new pile-supported bridge abutment. The subsurface conditions were very soft clay overlying steeply sloping granite bedrock with igneous intrusive dikes. So very hard, sound, crystalline bedrock. And the deep foundation alternatives were two different sizes of closed-toe pipes. Here you have the diameters and wall thicknesses in both imperial and SI units. All the steel components used were high-strength steel. And this is just a typical view of the site, some of the piles installed, some of them in the process of being installed. One of the unique things about these piles, they were otherwise generic constant diameter steel pipe piles, is that there was a fabricated, what we call toe stinger, that was added onto the flat plate toe closure. And this stinger had two components, a wide flange section and a proprietary cast steel point. And this is what they look like. You had the fairly thick steel plate to close off the toe of the pile. And then you had this wide flange section stub as an extension. And then welded to the end of this stub to complete the stinger, as we call it, was this proprietary cast steel point. So these cast steel points, they're made out of very high strength steel. As you see, they have teeth that are cast into them. And the idea is that when you have a sloping bedrock condition, that to prevent the toe of the pile from sliding along the bedrock and to help the pile bite into the bedrock, if you will, that these tips with the points will enable that. So that's the purpose for using the stinger in this case, was to try to make sure that the piles did not slide along the bedrock surface, but would bite into the rock. Well, unfortunately, both dynamic measurements and post-driving internal inspection of the piles indicated things did not work out as planned. And specifically, some of the smaller diameter pipes failed due to buckling because they did not seat on the steeply sloping rock as was desired. And this is what one of the buckled piles looks like as it was being extracted for inspection. And before we discuss things further, I want to highlight that note that these are spiral welded pipe. Right, you can see the factory welds here on the buckled pile. You can see the factory welds here on the partially installed pile. And again, I'm emphasizing this to highlight just how far they have come with the quality of spiral welded pipe. Again, in the early years, spiral welded pipe was deprecated for pipe piles because very often during driving, these welds would simply split. And that's why people specify seamless pipe. But certainly they have improved the manufacturing quality control of spiral welded pipe so that, as you could see, again, a classic case where the pile is yielded and buckled, but the weld did not fail. Here you see a pile that is buckled in what, 1, 2, 3 places. Here we're looking from head to toe, and you can see a couple of places where the pile is buckled. If we look from toe to head, we could see, again, a couple of places where the pile is buckled. Well, that was interesting. Certainly quite surprising was that not even the cast steel point with the points on it were immune to yielding. And here you see one of the cast steel points, and again, these are designed so that these teeth, if you will, grab into the rock. Well, you see what happened here. The rock was so strong, had such a high unconfined compressive strength, that even though this is high yield steel, as the pile slid along the sloping rock surface, this high strength steel yielded and actually just spread as though you were spreading soft butter or something like that. Very interesting. And I do want to thank Claire Waite, an engineer that I had the privilege to work with on another project in recent years, for sharing these photos and technical details with me. Well, let's journey back to Kennedy Airport, the New York area in general. There are some lessons, obviously, to be learned from this. And this is because the type of conditions they had at that site in Idaho were not unique. There's many, many places around the world where we have soft clay that transitions abruptly to hard, sound, steeply sloping bedrock, where these kind of problems can come up. For example, here in the general New York region, here's Kennedy Airport. If we look up and down the Hudson River Valley, a number of places where we have bridges or aqueducts crossing, you see that a very common stratigraphy is very steeply sloping rock. In this case, coming down about 700 feet, 200 meters below sea level. So the point I'm getting at is these sorts of ground conditions where this buckling might occur are certainly not unique to Idaho, and can be found in many parts of the world. And this is something we need to be concerned about. We generally don't think about the problem of buckling piles during installation, but obviously this is something that we need to recognize can occur. I'll just mention as an aside, I'm sure many of you have heard about the replacement of the bridge across the Tappan Zee, which is the widest place of the Hudson estuary. And this is the geologic profile when the original bridge was built in the 1950s. This was the much more refined geologic profile when the bridge was built just within the last few years. And by the way, I do want to point out that they did perform cone penetrometer soundings for this bridge project. You can do cone penetrometer soundings from the water, either using a barge or a jack-up rig. So, cone penetrometer is a device that is not limited to land. You certainly can use it in a marine environment. In fact, if you look at the offshore oil industry that installs structures in extremely deep water, they've actually invented a cone penetrometer that works remotely on the seabed surface. So really the cone penetrometer is an extraordinarily useful tool in geotechnical and structural engineering. Well, let's move on and talk about installation issues. And here I really want to focus on residual loads. I really think that these are one of the things that we need to rediscover as a profession. We've known about them since the 1950s. They've kind of fallen below our collective radar. And I want to illustrate to you why I think we need to pay a lot more attention to residual loads into the future. The reason for I feel we need to pay attention to residual loads are many and varied, and they really touch every single aspect of deep foundation performance. The thing I hope to illustrate to you here is that these are they're not just a problem with tapered piles at Kennedy Airport. That's the point I'm getting at. One of the claims you often hear is, well, residual loads are a pile phenomenon. I'm not driving piles. I don't have to worry about them. Well, Fellinius published a paper just a few years ago where he presented case histories where he showed that residual loads develop with drill shafts, board piles, if you will, as well as jack piles. So this then suggests that they may also develop with other types of deep foundation elements, including those that are currently very popular nowadays, such as micropiles and helical piles. It would seem that anything that is driven or pushed or torqued into the ground, certainly even drill shafts, where you excavate a hole in the ground, you have the potential to develop residual loads. So this tells me that this is something we should think about with all types of deep foundation elements. Another claim is that they're a geotechnical issue, and they go away as soon as we apply loads to the deep foundation. Well, we now recognize that this is really overly simplistic, and again, it is always unconservative and thus potentially unsafe to neglect residual loads, and I'll illustrate why. And this is because residual loads affect all aspects, geotechnical and structural, as well as when we perform resistance verification using load tests and dynamic measurements. So these are things we need to consider both in routine practice as well as academic research, and again, with all types of deep foundation elements. Well, let me discuss at some length how and why residual loads are so important and why we need to pay more attention to them into the future. First of all, with resistance forecasting, this is where we're trying to calculate beforehand how much axial compressive resistance that a deep foundation element will have once it's installed. Well, as I indicated earlier, certainly the fact that residual loads simply exist in and of itself calls into the question, how accurate are the traditional resistance forecasting methodologies we have? Because all of these methodologies are based on the assumption that whether you're driving a pile or installing a drilled shaft or a jack pile or whatever, that once installed in the ground, that deep foundation element is internally stress-free and there's no shaft and toe resistance. Think about it. All of the methods that we currently use routinely assume that, okay, I have this pile, I have this drilled shaft in the ground, there's no toe resistance, there's no shaft resistance, there's no stress inside of it because I haven't applied an axial load. And that's simply wrong. The material of which the pile or whatever is composed is going to have an initial compressive stress on it. There's going to be shaft resistance, both drag load and resistance, and there's going to be toe resistance. So our basic assumption is simply wrong. As I said, I think there's a point to be made that perhaps all types of deep foundations are never initially stress-free. And I'm going to show you some case histories where the drag loads were so important that they persisted all the way to the geotechnical ultimate limit state. The point I'm getting at, residual loads don't magically disappear once we start to apply load to the head of a deep foundation. And again, I've showed you this before, but this is just to refresh our memories as to this is what we're talking about. After the deep foundation is installed in the ground, even though there's no applied load at the head, we have compressive forces within the shaft, and we have a toe resistance. The upper portion is subjected to drag loads, the lower portion of the shaft has resistance, and we have a toe resistance. This is a test pile that was tested back in 1969 at Holmen Island, Norway, by the Norwegian Geotechnical Institute. And I'm going to be using the KH and KH over K0 ratios that I've talked about previously. And they relate to both drag load and resistance. So where these parameters are negative, this indicates a drag load. Where they're positive, this indicates resistance. So if we look at this pile, and by the way, this was a standard pile in Norway at the time, a precast concrete pile, constant diameter, called a Brynildsen pile. And as you can see, is about 16 meters, about 50 some odd feet embedded length. And in this case, the residual loads they measured after installation, this is all drag load. That's what this dash green curve is showing you. Here's the neutral plane. This was all resistance along the shaft. What you don't see here is the toe resistance. There was some initial toe resistance. So the toe resistance plus the shaft resistance exactly balanced out the drag load at this neutral plane. And I should point out that there was very high confidence in these drag loads because since these were precast concrete piles, they were instrumented while they were being manufactured and prior to driving. And then the piles were extracted and the zero readings were double checked. So there's a very, very high degree of confidence in all of these measured results I'm showing you with these Holmen Island piles from 1969. So they loaded this pile in compression to what they called Q90, which is how they defined the geotechnical ultimate limit state or failure load at the time. And there was about 2.5 inches, 65 millimeters of pile head settlement. So a significant amount of settlement. The interesting thing is when they got to 1/2 of the failure load, and I'm emphasizing this because they assumed that this was the maximum service load level on production piles. Notice that there was still, and that's the red curve you see here, this is at half the failure load in the load test. Notice how much drag load still exists. The neutral plane had only moved up from about here to here. So what I'm showing you here is, contrary to what some people have said, residual loads don't magically disappear when you apply a load to the head of the deep foundation. In this case, the pile was halfway loaded to failure and it still had a very significant drag load on it. And in fact, the drag load did not disappear completely until they loaded this pile to a geotechnical failure. That's what we're seeing here. They had to load this pile to failure. They had to make it settle 65 millimeters, 2.5 inches roughly at the head to cause all this drag load to go from here to here, just to zero out the drag load. And of course you develop more resistance down here, and there was more resistance at the toe as well. So while this was an extreme case, it still illustrates the point that drag loads can persist all the way until the point of geotechnical failure in axial compression under the right conditions. And by the way, the conditions here were a fairly loose sand, so these were coarse grained soil conditions. Resistance verification, construction quality assurance. I want to show you that residual loads can be a factor in load tests as well as dynamic measurements. Residual loads affect the stiffness of the deep foundation in the ground, and therefore the shape of the static load curve. And because of this, it affects our interpretation of the failure load. Okay, keep in mind that the way that we typically define the geotechnical failure load or ultimate limit state of a deep foundation is based on some settlement criterion, whether it's the Davison offset limit method that's popular in the United States, or it's a toe settlement criterion that's popular in Europe. It's based on system stiffness, which, as we'll see, is significantly affected by residual loads. What concerns me is that there's decades of load tests where we have not considered the effect of residual loads on the interpretation. And again, because we use load tests to verify and calibrate resistance forecasting methods, that really calls into question whether these resistance forecasting methods that we use now routinely in practice, if they have some errors built into them because we did not properly consider residual loads. So what I want to illustrate now is, okay, what happens to these residual loads as we apply a load in a load test? And I want to first illustrate it using theoretical concepts, and then I'm going to illustrate it using an actual case history. So if we look at an upper portion of a shaft where we have drag load existing, the traditional assumption in all of our analytical methods is that there is no shaft resistance. We start out at zero load, zero displacement, and that as we apply a load to the head of the pile or whatever type of deep foundation we have, we load this up to a geotechnical failure. Well, the reality is, in the upper portion here, due to drag loads, we're starting down here. Right? Here's the negative shaft resistance, the negative skin friction, as people like to call it, and I'm calling this drag load in this case. So we start from here, and as we apply load to the head, we have to first zero out the drag load before we can continue on with positive shaft friction and resistance. If we look at the lower portion of the shaft, that we have some initial resistance. Again, the traditional assumption we make in practice, we start with zero resistance, and then we go to failure. Well, the reality is we already have some resistance mobilized, so that when we perform the load test, we only can mobilize some additional resistance. Finally, if we look at the tip resistance, this is a lot more complex. But nevertheless, traditionally we assume that, okay, when this is installed in the ground, there is no toe resistance. I now apply a load, and I go from zero to some toe resistance. Well, the reality is a lot more complex. In reality, during installation, let's say during pile driving, what happens in reality is we go from here to here, we stop pile driving, and we get a bit of rebound, but it never comes back to zero. So that means we have some toe resistance already locked in. That's what this point denotes. So that when we perform the load test, we're really starting from here. We go back up to the virgin curve, then continue down the virgin curve further. And keep on going. And I put the question marks here because there's some indication that in certain ground conditions, certainly coarse grained soil, we may not really get a traditional plunging type of failure. There may not be a well-defined failure load at the toe. So that's why I'm kind of leaving this vague at this point here. Well, let's look at a case history just to illustrate that this is not just some academic exercise. And I've selected a case history based on a jacked pile because I want you to see that it's not just a driven pile phenomenon. Residual loads are something we need to think about, be concerned about with all types of deep foundation elements. So this was a case history from a paper by Felinius. It was a site in Southeast Asia. As you can see, pile was jacked about 15 meters in the ground, about 50 feet, predominantly coarse grained soil conditions. And you could see that there was a fairly substantial residual load locked into this pile at the end of installation. Well, this is the static load test that they measured. They made measurements of load versus settlement at the head of the pile, along the shaft, and at the toe. So this was an instrumented static load test. And they inferred from this that there was a plunging type of failure. And again, a plunging failure is when essentially you have unrestrained settlement at a constant load. And if we apply the conventional, say, Davison offset limit method, we would interpret that the geotechnical failure load, or the geotechnical ultimate limit state in this case, was 6,400 kilonewtons, or about 1,400 kips. Well, this is the, if you will, real behavior if we consider residual loads. And one of the things we recognize right away is that in the real behavior, there is not a plunging failure. The shaft resistances are different. The toe resistances are different as well. Well, of course, the question is why the discrepancy? Well, the heart of it really is because in the real world, we have a residual toe load of about 1,000 kilonewtons, 225 kips. And the thing is that when you perform the static load test, the instruments think that the toe has no load on it. So the instruments say that the toe load begins at 0 and then develops resistance as the toe settles. Because again, in this case, the instruments were zeroed out after the pile was jacked in the ground. But in the real world, as far as the pile was concerned, the pile really doesn't know the difference between installation and the load test. And if you want to think about things simplistically from the deep foundation's perspective, it doesn't really know the difference between installation and a load test. As far as the deep foundation is concerned, the load test is, well, it's just picking up where the installation let off, or finished off. In this case, okay, you already jacked the pile into the ground 16 meters. All you're doing in the load test is jacking it into the ground another 60 millimeters. It's nothing different from the pile's perspective. So the point then is really this load test, what you measure in the load test or think you measured, really begins here. Because your static load test does not begin at 0 load. It begins at this residual load that's already locked into the toe. So when you installed that jack pile, you went from here to here, and then at the end of installation, you left off here. You had that 1,000 kilonewton, 225 kip load locked into the toe. And then when you started your load test, you began from here, went here and reloading, up to the virgin curve and then just kept on going down the virgin curve. And you notice this was a case where the tow resistance did not reach a true failure load. It's continuing to increase at a very slow rate, but still continuing to increase at the point that the test was terminated. So that's really the heart of what I'm trying to get at here is typically when we run a load test, we assume that shaft and tow resistances begin at zero load. In reality, they don't. From the perspective of the deep foundation element in the ground, the load test is simply you're picking up where you left off when you installed it. Well, to continue on with the discussion, if you perform the Davison offset limit here, you interpret a failure load, geotechnical failure load of 4,700 kilonewtons, about 1,100 kips, which is about 27% less than what you interpreted here. And you'll notice that the conventional load test gave you a stiffer response than the softer response you had here. And by the way, if you want to use the European criterion for tow movement as defining failure, you could see that there's a resistance between the load test and reality here when residual loads are taken into account. Again, this reality is smaller than what you think you have here. Then this goes back to what I said earlier. It's another version of what you see is not what you get. You think you have this in terms of pile resistance from a load test. This is what you really have. And I'm emphasizing this because more than ever we use LRFD in design. And what does LRFD demand? LRFD demands that every component of a system, of a structural system, every element has a unique quote-unquote failure load. Every element has a unique ULS, ultimate limit state value. So with LRFD, it's very important to, as best as you can, accurately estimate what this ULS value is for that component. And what I'm saying here is that in deep foundations, when we base this on some arbitrary settlement-based interpretation, what we think is the failure load geotechnically, something up here, something in excess of 6,000 kilonewtons, is not. It's something down here. It's more like in the range of about 5,000 kilonewtons. And again, that's true whether you want to use the Davison method that we seem to love in the United States or a tow limit criterion that is more popular in Europe. And again, another thing is that the traditional load test implied a plunging type of failure, which is not what is happening in reality. You're continuing to develop resistance with additional penetration, although it's occurring at a very slow rate. And if you think about it, it makes sense. Again, from the pile's perspective, it doesn't know the difference between that first 15 meters that you jacked it in the ground and the additional 70 millimeters that you load tested it into the ground. It still thinks you're pushing it into the ground, so it's going deeper and it is developing more resistance as it goes deeper. And that's what we're seeing here. And that's why the tow resistance does not max out, even though the shaft resistance, as we see, has peaked at peak strength. Then actually we've had some loss in shaft resistance as strength went from peak to the constant volume or critical state value here. This sort of drop off or strain softening is quite common with shaft resistance. Well, what about uplift loading? I'll just go through this quickly. Fellinius did not discuss this specifically, but we can use the same concepts to illustrate what happens with uplift loading with residual loads. With uplift loading for this upper part of the shaft that has a drag load on it, negative shaft friction initially, we're not starting from zero, we're starting from down here. So in a sense, this upper portion of the shaft, you've already, to a significant extent, you've already mobilized whatever that shaft is going to give you an uplift resistance. Where your uplift resistance is really coming from is the lower portion down here, where you have positive shaft friction. Because you're not starting from here and going this way, you're starting from up here. And now as you apply a load, you first have to reverse the sign of the resistance and develop now negative shaft resistance. So the point is with uplift loading, all of your uplift resistance is coming from the lower part down here, not from the part where there's drag load, because in a sense you've already gotten all the uplift resistance up here you're ever going to get. Generally we ignore the toe behavior and uplift, but I just want to illustrate to you that it's not just zero from the start, that we do have an initial compressive toe resistance. So as we apply an uplift load, this has to go down to zero. Now, whether it stays at zero or we develop some cavitation and some tensile resistance at the toe really depends on the type of soil we have, how rapidly we apply the load, things like that. Continuing on with illustrating how residual loads impact resistance verification or construction quality assurance. Certainly, as I've noted already, they affect the interpretation of instrumented static load tests. Anytime the instruments are installed during the pile process or zeroed out at some point in the process. And again, we saw this slide, but I'm just pointing out that when you have something, as in this case with the monotube piles at Kennedy Airport, the steel pipes were driven in the ground, then you put in the instruments and zeroed the instruments. And all they were doing were measuring the strains in the concrete. They completely missed the residual loads, so they're going to give you a completely incorrect picture of the distribution within that pile. And again, this calls into question the decades of using instrumented static loads in both practice and research for calibrating resistance calculation methodologies. Again, the beta method I talked about. And Fellinius illustrated this for that jacked pile example in his 2015 paper. He illustrated that these are the beta values they back calculated based on the incorrect instrument readings in the pile shaft. When you corrected those readings for residual loads, look at the difference in beta values. The beta values up here, where we had drag load, they're 1/2 of the values. The incorrect, or what Fellinius called false values, they're half the beta values that you got from the instrumentation. Down here, the beta value was greater than the instruments told you. So this is the point I'm getting at. We have probably decades of instrumented piles and drilled shafts and all types of deep foundations where we've back calculated beta values and this value and that value, but we've back calculated those values based on incorrect instrumentation readings. Instrumentation readings where the residual loads were not considered. So all these beta values that we now use in practice as being quote unquote correct. Why? Because again, the perception that a static load test is the gold standard. It's the correct answer. Well, those beta values are incorrect. So any calculation based on those beta values is going to be incorrect. We need to really correct decades of static load tests for residual loads. I'm not saying it's going to be easy, but certainly we really need to think about this issue. Well, Dynamic on-pile measurements are not immune to residual loads issues. In this paper, Felinius illustrated what happens in this case. This was the CAPWAP interpretation of the resistance distribution in a pile 143 days after driving, so taking into account restrike data. But the methodology does not consider the residual loads, which were fairly significant in this case. Again, this is all drag load till we get down to here. And this is the neutral plane in this case. And then this is resistance, and you see that there was some toe resistance. So the true distribution of resistance is the red curve, which, as you could see, is noticeably different from the CAPWAP result. So again, think about how routinely in practice when we do a CAPWAP analysis, we rely on not only the total resistance that is forecast, we rely on the depth-wise distribution between shaft and toe. And what I'm trying to show you here is that there's evidence to suggest that because the methodology does not take residual load into account, that distribution that you think you have is not what you see, is not what you get. Well, let's now move on to structural issues. Again, the point I'm making here is that historically people have said, well, residual loads are a geotechnical problem. They don't affect the structural aspects. Well, they do. And we've looked at this a little bit already, and I just want to reinforce that. One of the things I haven't mentioned previously is that because of residual loads, the maximum force in a deep foundation element is not necessarily at the head, which is typically what we assume. And again, let's go back to the Holman Island 1969 test pile. What we're looking at here is the axial force distribution in that pile. This is the dashed green curve is the residual load distribution. This red curve is the distribution at 1/2 of failure load, so theoretically the maximum load. The point I'm getting at is typically in any deep foundation, we assume that the maximum force, I'm not saying stress, the maximum force is at the head of that deep foundation element. And in this case, we assume, okay, I'm applying a load of 230 kilonewtons, 50 kips. This is the largest force anywhere in this deep foundation, in this pile. Well, it's not, because under this load, we still have a fairly significant drag load. The neutral plane is down here. So what we're saying is that the force in this pile is this 230 kilonewtons plus all of this drag load added to it down to the neutral plane. All right? Again, this is just like a down drag situation as if the ground were settling relative to the pile. Except in this case, it's the pile that went up relative to the ground during driving. So that's what's causing the drag load. So the maximum load on the pile is the 230 plus all of this drag load along the shaft down to the neutral plane, which in this case works out to be 275 kilonewtons, 60 kips, or 20% increase. So that's a significant increase. You think that this is the maximum load up here. In reality, it's down here because of the residual. Well, obviously, we see there's implications with the design of the deep foundation as a structure. And again, coming back to a point I made earlier, that when you have a deep foundation with a composite or multi-component cross-section, like a concrete-filled monotube or taper tube pile, that you could be off on stress calculations. And again, I'm just showing you what I showed you previously, that the theoretical load distribution that we always use is wrong because it neglects residual loads. the actual stress and load distribution can be quite a bit different. In this case, in the steel pipe, you get a significant overstress in places. Within the concrete core, you get a significant understress. What are some of the conclusions we draw from this? Well, I don't want you to think that residual loads are always a negative. I tried to show you the negative consequences of ignoring residual loads. But the residual loads themselves, or in and of themselves, they're not negative. They're simply part of life, their nature. I mean, think about it in the context of structural steel if you have a rolled section. When you produce a wide flange section, we know that at the end of rolling that section, you're going to have what we call residual or mill or rolling stresses locked into that section. If you have a wide flange beam resting on the ground with no load on it, it still has some stresses in parts of that member. Simply an artifact of manufacturing that wide flange section. And it's the same thing with residual loads. I think we need to simply realize that when we create a deep foundation in the ground, whether we drive it, we jack it, we torque it, we drill it, but simply the process of creating a deep foundation in the ground is going to lock in some residual loads. Now, yes, they're certainly greatest for driven piles, especially tapered piles, but they're going to affect all deep foundations, and we simply need to take these things into account in our analysis and design as appropriate. If you think about it, there's actually a positive aspect to residual loads. To a certain extent, it's almost as if we should be encouraging residual loads. Why? Well, think of it in the context of why do we pre-stress reinforced Portland cement concrete? We wouldn't pre-stress concrete if we didn't have a benefit from it. And in that context, residual loads are actually our friend. And the more residual loads, the better, to be honest, as I'll point out to you. Residual loads are positive because they stiffen the overall load settlement behavior in axial compression. Yes, they do make it a bit worse in an axial uplift. They make it softer. But in axial compression, you have a stiffer behavior. And you have a stiffer behavior because the residual loads essentially preload the toe resistance to some extent. In extreme cases, as I showed you with those monotube piles at Kennedy Airport, we pre-stressed 100% of the ultimate toe resistance. You couldn't get any more if you tried. So residual loads preload the toe resistance, and that's especially true for piles and even more so for tapered piles. The net result is that when you put a post-installation load on this, that load is going to be carried by load transfer along the shaft, not the toe. This is Felinius's interpretation of those Holmen Island, Norway, 1969 test piles. And in this case, he's just showing you, and they installed both a partially tapered and a tapered pile. The tapered pile, it was only the lower half of the pile was tapered in a very small taper angle, about 0.29 degrees, about that of a timber pile. So there wasn't a lot of taper to this pile. But there was a lot of difference between the constant diameter pile and the tapered pile. If we look at the residual loads, the red curve is the residual load in the constant diameter pile. The blue curve is the residual load in the tapered pile. Big difference. And it's all within the tapered section. The thing I'm pointing out here is that all things being equal, if you have basically identical piles, constant diameter and tapered side by side, the tapered pile in coarse grained soils is going to develop more residual load, and it's all going to be due to this taper benefit. But it actually works in our favor. This is not a negative. This works in our favor as long as we take it into account properly. The reason that residual load works in our favor by pre-stressing the toe is we know that the load settlement behavior of the toe of any type of deep foundation is inherently softer than shaft behavior. I mean, we've known this for a very long time. Shaft behavior is always a much, much stiffer load settlement behavior compared to toe behavior. So in a sense, by pre-stressing and pre-settling the toe resistance, you're forcing the shaft to do more of the load transfer, and that's going to produce a stiffer overall system response, which is a good thing. Here in the United States, the driven pile industry has for a long time had a motto that a driven pile is a tested pile. The concept being that simply by driving a pile into the ground, you have some assurance that it has some axial compressive resistance. Well, I think we can legitimately add to that a driven pile is a pre-settled pile, simply because a driven pile locks in more residual load than any other type of deep foundation. And taper makes it even better. Quite simply, no type of deep foundation will generate more relative residual load than a tapered driven pile. And as long as we have properly accounted for those residual loads, that residual load is very definitely a benefit because it gives us an overall much, much stiffer axial compressive response. And that's always beneficial in practice. Okay, the next topic I want to talk about is the post-installation geotechnical and structural resistance to externally applied axial loads. This is how do we calculate what the resistance is to, say, compressive loads. In my opinion, the overarching issue that we should, as a profession, address in the future is the traditional presumption that all deep foundation elements have somehow have a unique single-value geotechnical ultimate limit state or failure value. I think it's a fair statement to say that that is a myth. The perception that no matter what type of deep foundation you have, that when you load it in axial compression, that it only ever has a single quote-unquote failure load, that is simply a myth. I understand that LRFD design demands a failure load, but that still is a myth. The problem is with the LRFD method, not with real-world behavior. And I say this so emphatically because the reality is that the geotechnical failure load or ultimate limit state of any deep foundation element is a range of values at best. And it's a range of values for a very wide range of reasons. There are some people who feel that the ultimate limit state does not exist at all geotechnically, that there simply is no such thing as failure when it comes to a deep foundation element. I don't intend to have an opinion on this one way or the other. That's not the point of this presentation. The point is that there is always a range in failure values. And I don't want to just say it. I want to give you some reasons why I feel that statement. The relevant considerations include the following. Again, as I've said now several times, everyone thinks that the static load test is the gold standard for defining the geotechnical ULS. You run a load test, this is the failure load, this is the answer. The reality is I've showed you that depending on the hardware you use, the setup you use, do you use jack pressure, do you use a load cell, the procedure, how quickly do you apply a load, how slowly do you apply a load, all of these variables are going to produce a different load settlement outcome. You change one thing, you're going to get a different load settlement outcome. So that's just from the testing part of it, not even any interpretation. And again, I've shown you this slide previously. This just shows, just from the hardware that is used to measure the load, to measure the settlement, you're going to get some range in failure loads. It's not this, it's not this, it's some range. As I've now said several times, residual loads are really the de facto initial start of the static load test. When you perform a static load test on any type of deep foundation, you think you're starting from no stresses in the shaft, no shaft resistance, no toe resistance, but you're not. There's initial stresses and resistance already locked in. And as far as that deep foundation is concerned, you're just picking up where you left off in terms of installation. You know, you drive a pile 50 feet in the ground and then you run a load test and you push it in the ground another 2 inches. As far as the pile is concerned, you drove it into the ground 50 feet 2 inches. It doesn't differentiate the load test as being something special or unique. And again, I showed you this with a case history on a jack pile where the traditional load tests assume we start here, but in reality, you're starting somewhere already along the load settlement curve of the toe. Even if you have a single load test curve, how that is interpreted for the failure load, I mean, we've known for decades that there's maybe 10, 12 methods, possibly even more, for interpreting a single curve as to what constitutes the failure. And you see in this example of a drilled shaft bored pile that the range in interpretations is over 200%. And that's nothing to do with, you know, whether you use the load cell or jack pressure or how you measure the settlements or things like that. This is just in the interpretation of the curve. What I'd really like to focus on is the physical mechanisms by which deep foundations develop resistance. It's important to understand that the way we say that shaft load develops or toe load develops, these concepts go back to the 1950s. 1950s is, I think, when what we can call modern foundation engineering began to develop. So the way that we think that toe resistance develops, the way we think shaft resistance develops, these concepts go back almost 70 years now. And if we look at these assumptions, these models that we use in light of what we have learned in the last 70 years, they're inaccurate, they're incomplete, and in some cases just plain incorrect. And thus they need to be revised and updated. So what I'm saying here is that we need a zero-based reassessment of how we model the shaft and toe resistance of deep foundations. Okay, let's begin with the basic case of a constant perimeter shaft of a deep foundation element that is subjected to axial compressive loading. I've showed you this view previously. This is from the work of Rubinski, where he placed lead shot within the sand, and the light-colored exposure is the position prior to loading, the dark-colored after loading. And as I noted earlier in this presentation, the traditional assumption with regard to the traditional resistance mechanism of shaft resistance due to sliding friction assumes that the ground somehow magically remains fixed in space, does not move, but the deep foundation element goes down, and we therefore develop simple Coulomb or dry friction along the assumed planar interface defined by the outside of the shaft and the surrounding ground. Well, again, as I noted earlier, this is simply incorrect. The reality is that the load transfer between the shaft of a deep foundation element and the surrounding ground is occurring as vertical shearing within a zone. And you can see this distorted zone of soil. That is where the shearing is occurring, and this shearing does progress outward from that, radially outward from that, so that the adjacent ground settles along with the shaft, but the shaft at some point settles more. There is some relative displacement, but the ground is certainly not magically fixed in space. So the point I'm getting at here is that the traditional physical model and mechanism that we use for the traditional mechanism of shaft resistance due to sliding friction is simply incorrect. It is not sliding along a planar interface where the ground remains fixed in space and the deep foundation settles. Both the ground and the deep foundation settle, and there is a zone of shearing around the deep foundation element. And this behavior has been found, it was not just exclusive to Rybinski, it's been found independently by researchers around the world for over 50 years. I mean, Rybinski did his work in Canada. This is the work of Manandhar and Yasufuku in Japan, and you see the same behavior. These researchers use colored sand, but again, you notice that there is the zone of shearing between the shaft and the soil. The soil settles as well as the shaft, and again over here you have a zone of shearing. The soil settles as well as the shaft. So clearly we need to change the way that we model and analyze shaft resistance for a constant perimeter shaft. Moving on now to tapered shafts. Tapered piles have been used for over 7,000 years. I mean, humans have been driving timber piles, which are inherently tapered, for over 7,000 years. But the taper benefit that I mentioned earlier is still underappreciated and underutilized around the world. There are areas, especially here in the United States, where in the eastern half of the United States, where we have long recognized the benefit of tapered piles, but much of the rest of the world simply has not fully recognized their benefit. And as I said earlier, if you look at U.S. patent filings going back to the late 19th century, and all of these patents, by the way, were filed by contractors. They were not filed by design engineers. They were not filed by academicians. They were filed by the very people who drove piles every day as a living. So these people who installed piles learned long before there was modern saw mechanics that there was a benefit to tapered piles. When modern foundation engineering began to evolve in the 1950s, there was some half-hearted recognition of taper benefit, but it was just using what I call a one-size-fits-all empirical coefficient applied to shaft sliding friction. Really did not capture what was really happening with tapered piles. Nordland was the first one. His seminal contribution to the profession was the recognition that there was a unique physical mechanism that I call wedging that occurs with tapered piles. And by the way, while most people are familiar with Nordland's original 1963 work, a lot of people don't realize that he actually revised his methodology in 1979. So when people refer to the Nordland method, you have to ask which one, because there's a 1963 version and a 1979 version. But Nordland used a fairly crude two-dimensional passive lateral earth pressure model to model this wedging. It certainly was better than a one-size-fits-all approach to things, but is still in need of improvement. To illustrate what this physical mechanism of wedging looks like, if we just look at, again, some arbitrary fixed plane in space in the ground, what wedging is all about, it involves the creation followed by additional expansion of a volume relative to this fixed plane in space. And for a pile that is driven into the ground, there are two very distinct stages of wedging, and that's very important because these two stages provide a cumulative synergistic taper benefit that you don't get with say a drilled taper deep foundation. To get the maximum taper benefit, you have to have a driven pile. And you can see that intuitively, just by looking at this animated graphic, that when you drive a tapered pile in the ground, the toe creates a hole in the ground, and then as you continue to drive the tapered pile, you could see that you continue to open up a ever-expanding volume at some relative to some fixed point in space. Then after that pile has been installed in the ground and now you apply axial compressive loading, notice that you're going to expand this volume further. That's one of the very unique things about a tapered deep foundation, is that as you load it in axial compression, it is actually getting more resistance. And that is really a unique aspect to tapered deep foundations. And again, you could see that visually here. That imagine this is simulating now applying an axial compressive load, the pile is, or whatever type of tapered deep foundation element is settling. You are continuing to expand this pile or deep foundation element relative to the surrounding ground, and as a result increasing radial pressures around that element. And this is just a static version of the preceding animated graphic to illustrate that essentially what happens: stage 1 wedging occurs during driving, stage 2 wedging occurs during post-installation axial compressive loading, that you are expanding the volume of this pile or deep foundation element relative to the surrounding ground, and in the process increasing this pressure. And this is essentially the same thing that happens with a pressure meter. We've all seen the results of pressure meter testing, where you expand. The pressure meter happens to be a cylinder that we expand. This is just expanding a cylinder in a little bit different way. But you continue to increase this radial pressure until you reach some limiting pressure in a pressure meter test. Now, it happens with a tapered deep foundation that you would have to load it to very large amounts of settlement in order to reach this limiting pressure. 1993, Geotechnical and Moore also published what I think is a seminal paper that advanced the understanding of tapered piles and wedging, because they now, instead of using Nordland's passive earth pressure model of a retaining wall, based their work on cylindrical cavity mechanics. There are some significant omissions, I think, in Geotechnical and Moore's work, but it is still very important to the knowledge base because of their use of cylindrical cavity mechanics. So they were on the right track in terms of identifying cylindrical cavity mechanics as a physical and mathematical model for wedging. They just did not apply it completely incorrectly, in my opinion. And this is just an animation of what cylindrical cavity mechanics is all about. Again, relative to some arbitrary fixed plane of space, you have a cylindrical cavity and you expand it radially, and in the process of doing that, you increase the radial pressure acting on that cavity. And again, this is exactly what happens in a pressure meter test, so that we know that this mechanism actually develops in the real world. And this is just a very good model, I feel, for what happens with tapered piles. I feel very strongly that what I call shaft resistance due to wedging that occurs with tapered piles and tapered deep foundation elements in general. It's just that this wedging is substantially greater with a tapered pile, because you get wedging during driving as well as loading, whereas if you had, for example, a tapered drill shaft, you would only get the taper benefit during loading, which is much, much less. But in any event, the shaft resistance due to wedging that occurs around the shaft of a tapered pile and modeled using cylindrical cavity mechanics, I felt for a very long time should be formally recognized as what I call a third resistance mechanism for deep foundations. Since the 1950s, we've had two classical resistance mechanisms for any type of deep foundation element. We have shaft resistance due to sliding friction. We have toe resistance due to end bearing. Shaft resistance due to wedging is distinctly different from shaft resistance due to sliding friction. It is not simply an empirical correction to shaft resistance due to sliding friction, as early researchers such as Nordland and Meyerhoff and Kodakara and Moore have assumed. And I'll give you some very good reasons why it is a very distinctive mechanism. First of all, during installation, and here now we're talking strictly about driven piles, there are radial stresses acting along the shaft-sole interface that contribute to the post-installation shaft resistance continue to increase behind the toe of a tapered pile as the result of the additional cavity expansion I just illustrated. If you have a constant perimeter pile, whether it's circular in cross-section or square in cross-section, doesn't matter, these radial stresses remain constant once the toe of the pile creates a hole in the ground, if you will. During axial compressive loading, the shaft resistance of a tapered pile increases further because, as I've showed you, as this pile continues to settle into the ground, you're expanding this cavity further. And this cavity does not reach a limiting pressure. You'd have to go to settlements well beyond those that would occur under service loads with a pile to develop the limiting pressure. If you look at a typical pressure meter test result and you look at the percentage of cavity expansion required to reach the limiting pressure, it is substantially greater than any cavity expansion you're ever going to get with a tapered deep foundation. On the other hand, if you have a constant perimeter pile, as that pile settles, the shaft resistance due to sliding friction maxes out under very small settlements. And as I showed you in that load test for the jack pile, not only does it max out, it will actually exhibit strain softening. It will actually decrease somewhat as the soil strength transitions from peak to constant volume or critical state values. Again, let me show you an animated graphic to illustrate the points I'm making here. The overall point I'm trying to make is these are two very distinct resistance mechanisms along the shaft of a deep foundation element. Wedging is not a modification of sliding friction. If we look at the traditional shaft resistance due to sliding friction that happens with a constant perimeter deep foundation element, if this is a constant diameter pile, for example, as you drive it in the ground, the toe of the pile creates a cavity in the ground. You get a radial stress around the shaft, but then as you continue to drive this constant diameter pile, this radial stress stays constant. On the other hand, when you drive a tapered pile, the toe opens a cavity in the ground, you have a radial stress, but then as you continue to drive this tapered pile, notice how this radial stress is increasing further. This is what I call stage 1 wedging and is the stage 1 tapered benefit of a tapered pile. Now we move on to axial compressive loading. Whether it's in a load test or under service loads in the actual structure, it doesn't matter. Again, if you have, say, a constant diameter pile, that radial stress acting on the pile shaft is going to remain constant no matter how much load you apply and how much this shaft settles. In fact, because the strength along here goes from the peak to the constant volume or critical state value, you're going to actually lose a bit of shaft resistance. We see that behavior time and time again. You get a peak and then you get a little bit of strain softening and it drops off to a constant value. Look what happens with a tapered pile. If this is a load application to a tapered pile, as that pile settles, you're increasing the radial stress even more. I mean, that's a really, to me, an amazing thing that literally what you're saying, as you're loading a tapered pile, it's actually gaining more resistance. It's getting stronger the more you load it. And I think you'd be hard-pressed to find any other type of deep foundation element that basically gets stronger the more load you apply to it. And that to me is really the unique aspect of a tapered pile. And that's what makes, in my mind, tapered piles very special. As I said, people have known this since the late 19th century. I at a loss to understand why we don't use tapered piles more in practice. Finally, if we move on to toe resistance due to end bearing, again, this is another part of Rubinski's work, and you could see the pattern, by the way, of the, this is showing what happens. You could see the pattern of the lead shot tracing the pattern of soil displacement under simulated axial loading. The dashed line here is the original surface of the soil. As you load this model pile, the soil settles. Again, this shows very conclusively the point I'm making, that shaft resistance due to sliding friction along a constant perimeter deep foundation. All this load transfer is occurring within a zone of finite thickness. It is not occurring at a one-dimensional planar interface. You have an entire zone here, some radial distance away from the deep foundation. But I want to focus on toe resistance now. Look at the lead shot under the toe. See how Rubinski did not place the lead shot in this very nice triangular wedge pattern. Nature found this pattern on its own. Nature created this soil wedge that is very nicely defined by the lead shot on its own. And the point I'm trying to make here is that if you look at this failure mechanism beneath the toe, this does not in any way, shape, or form resemblance the classical bearing capacity solutions that we have used since the 1950s for toe resistance. And those classical bearing capacity theories, of course, as we know, assume that the vertical overburden stress is what governs bearing capacity. Now, those bearing capacity theories may work very well for shallow foundations, and indeed with shallow foundations very often we will see the classical failure mechanism, but we don't see that under deep foundations. So again, the point I'm trying to make here is that we really need to revisit and revise the things we've been doing for the last 70 years with respect to toe resistance. I think an argument can be made that a different physical mechanism and model that we call spherical cavity expansion is better suited for deep foundations. And what I'm trying to show you here is that this wedge of soil that basically develops naturally beneath the toe under axial compression, that what it is doing, it is creating two spherical zones of cavity expansion around the toe. And this is nothing new. I mean, Vesage first proposed cylindrical cavity expansion for toe bearing at deep foundations. I believe the original publication was 1970. This happens to come from a somewhat later publication of his. But my point is this idea of using a different, better physical mechanism and model and mathematical model for toe resistance is not new. It's probably 50 years old at this point. The interesting thing about spherical cavity expansion is that it is the horizontal effective stress that governs the behavior. And I think you could see that. If you're trying to basically, think of this as basically blowing up a balloon around the toe of the deep foundation element. That's essentially what spherical cavity expansion is. You're trying to blow up a balloon around the toe of a deep foundation. And it stands to reason that as you're trying to expand this balloon, it is the horizontal stresses that govern, and therefore KO. And you can see why earlier in this presentation I made a point of emphasizing the importance of, when you do site characterization, that you estimate K sub O in the ground prior to foundation construction. And again, there's no in situ testing device better suited for this than the cone penetrometer. either a Pisa cone or a seismic Pisa cone. Further proof that KO is very important for tow resistance of all types of deep foundations, not just driven piles, is from research related to cone penetrometers. And researchers have found time and time again that what controls Q sub C, the uncorrected tip resistance of a cone penetrometer, is not the vertical effective stress, it is the horizontal effective stress. And therefore, by implication, K sub O. So, I repeat again something I've mentioned a couple times now in this presentation, that K sub O and horizontal stress really dominate all aspects of deep foundations, not just driven piles. No matter what type of deep foundation element you have, whether it's constant perimeter shaft, a tapered shaft, or tow resistance, any of those three resistance mechanisms, K sub O is the governing soil property in all types of soil, coarse-grained and fine. So the bottom line conclusion I've reached is that it really needs to be a zero-based reassessment and revision of the geotechnical resistance mechanisms, and these need to explicitly consider residual loads. Residual loads, as I said, are simply the starting point of any post-installation load application. Whether you're performing a load test, whether you're applying service loads from an actual structure, you are not starting from a zero force in the deep foundation, zero resistance along the shaft and toe situation, as we traditionally assume. It is not a zero force, zero stress starting point. There's forces and stresses and resistance and drag loads initially locked in. That's the starting point, and that needs to be the starting point in our analytical methodologies. With respect to residual loads, I think a better understanding of residual loads may hold the key to understanding why piles in coarse-grained soils tend to increase axial compressive resistance over time. I think there may be some link to residual loads. You know, when I've talked about residual loads in this presentation, I've kind of portrayed them as being, okay, they exist after installation and that's it, they're a constant value. I think it's quite possible that these residual loads may actually change after initial installation. I think the only reason we simply haven't studied it. You know, when people have actually either measured residual loads or tried to back calculate residual loads, it's for a single snapshot or point in time. To the best of my knowledge, nobody has ever said, gee, do residual loads change over time? If I drive this pile in the ground today, what are the residual loads an hour from now, a day from now, a week from now, a month from now? Nobody, as far as I know, has looked at temporal changes in residual loads. And perhaps if they do change, especially since they mobilize a substantial amount of tow resistance, that perhaps this is why we're seeing an apparent change in resistance of piles. It's important to understand that the temporal increase in pile resistance is linked to stiffness, not to strength. This is not a pore pressure reconsolidation type of phenomenon as occurs in fine-grained soils. When you have coarse-grained soils, there are changes in soil stiffness going on, and again, we have not studied this to date. I think it'd be very fruitful research if we would go back. We basically need to reestablish contact with residual loads. As I said, we've known they've existed since the 1950s. We need to look at some of this research from the 1980s, perhaps revise it, expand on it, update it with current knowledge. I think it would be very useful to have some instrumented piles and to monitor how residual loads change over time. In other words, after initial driving, to actually look at changes in residual loads before you even think about applying an external load. And concomitant with looking at temporal changes of residual loads, I think at the same time we need to look at changes in the small strain shear modulus around a pile. So for example, you might drive a instrumented pile in the ground and then measure the residual loads an hour later. And when you measure those loads an hour later, you take a seismic piezo cone sounding. And then you come back a day later and you measure the residual loads, take a seismic piezo cone sounding. And then repeat this process of measuring residual loads and performing a seismic piezo cone sounding a week later, a month later, etc. And I think it'd be very interesting to see how those residual loads and how those small strain shear stiffnesses may change over time. I think this may hold a key to our better understanding of these time changes that affect driven piles and coarse grained soils. Hopefully I've showed you that this idea that there was always a magical single geotechnical failure load ultimate limit state, that it's a myth, that this will open our mind to focusing more on the load settlement behavior, which if you think about it, we've always done this with shallow foundations since the 1950s. We long ago learned that with shallow foundations, we tend to focus more on the load settlement behavior than on the bearing capacity. We haven't abandoned bearing capacity. We still check bearing capacity. And I'm not saying we should abandon the idea of a failure or ultimate geotechnical load with a deep foundation, but we shouldn't focus on it exclusively at the expense of considering settlements. And the simple reason is that the geotechnical ULS of any type of deep foundation is in general some range in values. It's not a single value. Some of these things that I'm suggesting here about focusing more on settlement and not this failure load, I'm certainly not alone in this. I mean, this is a position that Fellinius has taken for quite a long time now. If we look at load settlement behavior, how we might go about this, as I hopefully have shown you now, that load transfer between the shaft of a deep foundation and the surrounding ground is vertical shearing within the zone of soil, not simple slippage. You get a settlement trough that surrounds the deep foundation. And by the way, I think you could see why, as I pointed out earlier, that the traditional way that we measure the settlement at the head of a deep foundation during a load test with dial gauges and tension wires and mirrors and all that stuff, the support beams for those sorts of devices have to be placed reasonably close to the deep foundation element. But the point is unfortunately, those supports are going to settle somewhat when we apply the load to the deep foundation element. And that's why, as I've said, I found on a first-hand basis, not just at Kennedy Airport, from other load tests at other sites, that typically we underestimate settlements of deep foundations by about 10%. That's I think, a good ballpark number. There is a theory of elasticity solution that is called the Randolph-Roth problem. It's not just one publication, it's a series of publications several decades ago. And essentially the physical model that they used was one of imaginary cylinders of elastic material surrounding a deep foundation element. So the thing about the Randolph-Roth problem is that they assumed vertical shearing within an elastic medium, an idealized elastic medium around a deep foundation element as the behavioral mechanism. And that actually captures what is going on with actual deep foundations. The Randolph-Roth problem solutions have been used for deep foundations and adapted for use for some time now. This is nothing new, but I'm just pointing out that these solutions are interesting because they do capture the reality of what happens. And the bottom line I want to conclude this presentation with is that deep foundation behavior and axial compression is a settlement problem. And we really need to get away from this mindset of chasing after a single valued failure load because it simply doesn't exist. Unfortunately, more than ever with LRFD is kind of forcing us to chase after this myth of a single value failure load. I'm not saying we should abandon LRFD, but I don't think we should become so obsessed with LRFD that we lose sight of the real behavior of deep foundations. Well, if we open our minds to considering ground stiffness and load settlement behavior of deep foundations, that opens up the potential for new stiffness-based resistance forecasting methodologies. And this is the basic concept, that you perform, say, a seismic piezocone sounding and you get a depth-wise variation of the small strain of the shear wave velocity. And again, if you have ground conditions such that you cannot use a cone penetrometer, there are other invasive and non-invasive devices for measuring shear wave velocity as a function of depth. So if you're in soil with cobbles and boulders, if you're in rock, weathered rock, residual soils, whatever, there are methods that you could use that you can create a profile of shear wave velocity versus depth. Again, I suggest that you watch Professor Stokey's webinar on the ISSMGE website if you've not done so already. Well, we can then convert those shear wave velocities to a small strain shear modulus profile, and then the concept is based on R&D. We can develop a methodology for forecasting the load settlement behavior. Well, this is not just an abstract concept. People have done this. And I'd just like to summarize what the process that's been published within the last few years is about. Again, we have our shear wave velocity profile, which gives us our small strain shear modulus profile. I'm just going to rotate that plot 90 degrees because this is how the original author showed it. So we're just showing this is the depth, this is the small strain shear modulus. You'll notice this author used G max instead of G naught. As they pointed out earlier, it's the same thing. Again, if you can't perform a seismic piezocone, you can obtain this profile using some other in situ testing device. Well, one of the things that's found is that if you look at static load tests on a wide variety of different types of deep foundations, that if you plot this on a semi-log plot, you plot settlement at the head of the deep foundation element versus the shear modulus degradation or reduction, you get this very nice S-shaped curve. And this should look familiar to geotechnical engineers because this is the type of plot we see, for example, if you run a resonant column test. Uses the same 5-cycle semi-log plot with resonant column. You're plotting shear modulus degradation as a function of shear strain. In this case, instead of plotting shear strain, we're plotting settlement at the head of the deep foundation. Well, you see the same overall pattern, but you can see by the different color of the symbols that different types of deep foundations differ somewhat. So if we segregate things based on deep foundation typology, this is just, we've replotted this using different axes, different parameters, but these results are essentially the same as you see up here. We see that we have a very nice trend for driven piles, a similar trend for augured cast in place piles, another trend for jack piles, another trend for drilled shafts, bored piles. And I do want to point out that this is not just limited to soil. This would be applicable to deep foundations and rock, in fact, in any type of ground condition. And what you get is you get an empirical relationship between shear modulus degradation and settlement at the head of the deep foundation element. And these different parameters, these are just empirical. They come from the specific plots shown here. Well, you can then use the Randolph-Roth problem, and this is just algebra. What we're showing here is that you have the load at the head of the deep foundation element, Q sub t in this notation, the settlement of the head, W sub t. This is just the shear modulus along the deep foundation element that you would get from this plot here. This is just algebra. It looks intimidating. It's just algebra. It's just, well, we got about half the Greek alphabet here, I think. But this just relates to the diameter of the pile, the Poisson ratio of the ground, the embedded length of the pile, etc. Well, what you get as a result, and it requires nothing more than a spreadsheet solution. I mean, you could really do this by hand, but why bother? It's so easy to do generically in a spreadsheet. Notice that you get the load versus settlement relationship. And again, I'm pointing out, I'm not against the concept of an ultimate limit state. It's just that it's really not a fixed number. It's a range in values. But notice that from a methodology such as this, we get a much better picture. We get a load settlement picture for the deep foundation. And if you really want a ULS, ultimate limit state failure value, to use, say, in an LRFD methodology, well, then you could apply some sort of interpretation to this. You want to base it on head settlement. You want to, as we do in the United States with the Davison method, if you want to base it on toe settlement as they prefer in Europe, it doesn't matter. You could just interpret this curve as you see fit. Well, this, as you can see, you get a really, what I call an integrated one-step forecasting methodology that gives you the entire load settlement range. We're not just chasing after a single failure value that, as I said, really doesn't exist in practice. The nice thing is this method is very easy to extend. I've already done it with tapered piles. We could extend it to, say, micro piles and helical piles, which are very popular to use these days. Again, any type of ground condition. There's potential to extend this to uplift loads, and I think also potential to use with existing foundations. There's a great emphasis nowadays, especially here in the United States with highway-related work, to reuse existing foundations where it makes economical sense. So, for example, if you had an existing deep foundation in the ground, you could perform a seismic pisocone. You can get a small strain shear modulus profile and then use that to estimate a load settlement response for that existing foundation element, perhaps. I want to point out that in order to generate the data that I showed you, to use this methodology, all you need is an ordinary static load test. It does not have to be an instrumented load test. All you need is an ordinary static load test where you measure the load, the applied load, and the settlement at the head of the deep foundation element. Does not have to be to a geotechnical failure. It could be to a lesser amount, and again, any type of ground condition. So again, just all you need is a shear modulus profile, static load test, and you can produce a result similar to this. I'm not saying that this is the ultimate methodology we should use. I'm really using this to illustrate the point that the concept of doing a stiffness settlement-based analysis of a deep foundation is not just theoretical or hypothetical concept or in the realm of academia. I mean, this is something that a practicing engineer could do today if she or he wanted. Finally, we shouldn't forget about the structural elements, the structural design of a composite multi-component deep foundation element, again, such as a steel pipe pile that's filled with concrete after driving. In terms of structural design, most people still use a traditional one-dimensional model for allocating forces and stresses. There is a three-dimensional model that I developed about 10 years ago. It's in the published literature. The benefit of that is, in addition to the axial stresses, you get radial stresses and radial displacements, and that could be very useful. But in either case, both the one-dimensional and three-dimensional model, they do need to be revised and improved, because both of them, unfortunately, are based on the assumption we start from a zero stress condition. And hopefully I've showed you that residual loads are something that we now need to consider with all types of deep foundations. So both of these models need to be revised to take into account residual loads and the fact that, for example, if you have a concrete filled pipe pile, that steel in that pipe pile is going to have a rather significant stress in it before you even place the concrete. And when you're going to apportion your loads between the steel and the concrete, you need to take that into account. And I think these are things we should be looking at with other types of deep foundations, such as micropiles. And the reason is simple. I've showed you this slide now a couple times, is that if we don't consider residual loads, you run the risk of overstressing the steel pipe component of a multi-component deep foundation element. Okay, I now want to talk about resistance verification, construction quality assurance. I think we need to recognize that static load tests are relatively costly, so we should maximize what we get from them. It's important to realize that the cost of a bad static load test is not much less than a good quality static load test. So if you cut corners to thinking you're saving your clients money, you're really not. And if you want some proof of this from others, I suggest that you watch some of the episodes of a webinar that is put on by the Deep Foundations Institute. I'm proud and pleased to say that I've been an independent charter member of the DFI since it was formed in the 1970s. DFI has had a webinar series called It's Money since late 2019 and continuing now into 2020. And each of these webinars hosts 3 different practitioners: design engineers, construction contractors, people who deal with deep foundations every day as part of making a living. And the theme of this webinar is that in the long run, performing load testing, good quality load testing, will always, always save the owner or the client money. Now, whether this is done during the design phase of a project, whether it's done in the early stages of construction, whether it's a big project or a small project. Again, as with good quality site characterization, hopefully I've shown you that this is not just a big project sort of thing. We could do good quality site characterization with very small, modest projects. And the same thing is true with good quality testing. That yes, good quality testing will cost the owner, client, some money, but they will more than make up for that in the savings of the deep foundation element. So never treat a static load test as a necessary evil or commodity just to be done at the least possible cost by a low bidder. Don't just follow the letter of the law, but the spirit of the law, if you will, to provide meaningful results. You should only test complete deep foundation elements. I mean, if the production piles are going to be concrete filled steel pipe, well, then you should only test concrete filled steel pipe, not just the steel pipe by itself. In this day and age, there's no excuse not to use an electronic load cell. There's absolutely no excuse that we should be doing static load tests using jack pressure measurements. Hopefully, I've showed you using real-world data that you will always overestimate the load on a deep foundation element by a significant amount, 20–25%. If you use jack pressure, and that is going to be on the unconservative side. You're going to think that that deep foundation carries 20–25% more load than it really can. And so now you're getting into potentially unsafe territory. I really think we need to develop some better ways to measure the settlement at the head of a deep foundation during a load test. Dial gauges, tension wires, and mirrors, these are 100-year-old technologies that really need to be retired. We've certainly done a lot with automated lasers in recent years for other aspects of geotechnical engineering, for supportive excavation, monitoring building settlements and displacements around excavations. I don't think there's any reason why we shouldn't be thinking about developing an automated laser to measure the settlement ahead of a deep foundation during a load test. Always apply loads in a monotonic manner. No unload reload cycles, no extended load holds. Just apply a load and fail the deep foundation element where appropriate. I think we need to get away from this load test to double design only. Again, you think you're saving your client, the owner, some money by not prolonging the load test, but I think you're really, in the end, you're costing them money. We should always load a deep foundation element to the geotechnical ultimate limit state or failure, unless there's a good reason. Certainly, if you have a drilled shaft socketed into hard sound bedrock, you're not going to load the bedrock to failure. You need to be reasonable. But certainly in any friction or floating deep foundation type of situation, we need to load it to the ultimate limit state. Several inches of head settlement, several tens of millimeters. I can't emphasize enough how important this is. Hopefully I've showed you in the history of Kennedy Airport that had we not loaded piles to the ultimate limit state, we would still be back in 1972 driving 30-ton timber piles. The only reason that nowadays we're driving taper tube piles that have ultimate resistances in excess of 1,000 kips is because we push the envelope. All right, so if we had not loaded deep foundations to the geotechnical ultimate limit state, we would never have known exactly how much we could extract from these deep foundations. I mean, think about it. At Kennedy Airport, they pushed the envelope on steel pipe piles to the point where the strength of the steel was now controlling the pile. That's almost unheard of. Usually with deep foundations, it's always the ground that controls the problem, not the structural components. But at Kennedy Airport, we've pushed the ground capacity to the limit, to the point where they literally had to design a new type of steel pipe to be able to withstand the geotechnical load. And to me, that's a very powerful message as to, by loading deep foundation elements to the geotechnical ultimate limit state where appropriate, in the end run, you're going to push the envelope of technology and ultimately save the owner, save the client money. That's why now when we drive one taper tube pile, it does the work of perhaps 8-ton timber piles from 30, 40, 50 years ago. Certainly, repeat load tests on the same deep foundation element should not, in general, be performed. This thing that, I don't like the load test today, I'll run a load test tomorrow and things will be better. That's a bad habit that simply should not be continued. There may be some compelling reasons at times to retest a deep foundation element, but when you do that, it should never be viewed as a new test. It should be viewed as a reload cycle of the original test, and you plot the load settlement behavior for that retesting as an addition to the load settlement behavior of the original test. Don't portray it as an entirely new test. We need to recognize, I've now made this point many times, residual loads are simply a fact of life. They're not going to go away. We can't wish them away by saying, well, in my analysis, I'm going to start at zero resistance, zero load in the pile. That's not going to make residual loads going to go away. They're still going to be there. They're still going to affect the behavior. So we need to take that into account. Certainly, if you perform instrumented load tests, you need to correct for the residual loads. And hopefully I've shown you or pointed out Fellenius's work, and Fellenius has shown you that residual loads affect not only driven piles, but drilled shafts, jack piles. They may well affect micro piles and helical piles as well. I'm not sure that anybody has ever looked into whether there are residual loads with micro piles, residual loads with helical piles. I think we need to look into that. I think there's certainly a good possibility that that is true. I mean, if you think about it with a helical pile, if you torque something into the ground and then stop torquing it, I think there's going to be some locked-in results from that torquing. I've talked about static load testing. We should think about the dynamic testing that we do, the dynamic methodologies. All the dynamic methodologies we have are based on the one-dimensional wave transmission in an elastic rod. And by the way, I know a lot of people think that one-dimensional wave mechanics goes back to Smith and his 1960 paper. Well, if you look at literature, you find that it really goes back to Isaacs in 1931. So we've been using, to some degree, we've been using one-dimensional wave mechanics to model deep foundations since 1930. That works in a lot of situations, but not when it comes to taper deep foundations. This third resistance mechanism of wedging is not well modeled by one-dimensional wave theory. One-dimensional wave theory assumes that as an elastic wave travels down a deep foundation element, it will only displace in the axial direction. And hopefully I've showed you with some animations that when you drive a tapered pile, you get axial and radial displacements. So I think we need to revise the wave equation and all the wave-based dynamic testing that we do on tapered piles to better model the wedging mechanism. We don't do that at present. Well, to bring this presentation to a conclusion, I want to talk a bit about people. I've talked a lot about inanimate objects and things, concepts. We should never lose sight of the fact that people are really the most important component and asset in the deep foundation industry. And certainly we have seen this in the foundation history at Kennedy Airport over the last 77 years and counting. Because of all the technological pushing of the envelope that has been done, it was done by a person or persons. I mean, advancements in technology don't happen in a vacuum. The taper tube pile was not developed in a vacuum. The use of on-pile dynamic measurements did not happen in a vacuum. These concepts were not developed in a vacuum. So the human element is really the one unifying factor in the history of the airport. And interestingly enough, it's really been a combination of stakeholders, design engineers trying new techniques, people involved in the materials and installation side of deep foundations, and owners and clients, developers, who are willing to take a chance, spend some money to push the envelope. Certainly since the 1980s, we need to acknowledge professional geologists who've really helped us to understand things such as East Coast United States seismicity and the seismicity of the New York area in general, and some of these things about reinterpretation of the glacial geology and the stratigraphy of the upper glacial aquifer. Our geological friends really need to be noted for their contributions. Certainly many people have been involved in the advances at Kennedy Airport, but there's three that certainly I'm aware of that I'd like to point out for their really seminal contributions. And I list them alphabetically. Jack Doherty, the late Stan Merjan, and Don York. And last but not least, I want to thank some former students who, in the course of their professional employment that took them to Kennedy Airport, provided me with some of the photos that I've used in this presentation, and I've acknowledged their contribution with these photos. And I also want to thank the specific geologists and engineers whose work I referenced in this presentation. I have included 3 slides worth of reference list. You can stop the presentation at your discretion and look these up. You can find many of these references online, often at no cost. So just wanted to point that out. And to wrap things up, I want to come back to the concept of change. As I said in the prologue of this presentation, to me, Kennedy Airport is a study in towers and change. And certainly we've seen that. We've seen how we've gone from the tower associated with the Idlewild Hotel around 1900 to the present day control tower. We've seen how we started with this very modest commercial airport in 1948 to these 21st century concepts for the latest redevelopment of the airport that is currently in the planning stages. We've seen how we've gone from driving timber piles with a steam hammer in the 1940s and beyond to installing taper tube piles with a hydraulic hammer, piles that carry 8 to 10 times per pile what a timber pile used to carry. From the analytical side, we've seen how when the airport was first started construction in 1943, in Terzagh's own words, when it came to deep foundations, there was absolutely no way to calculate beforehand what the load bearing of that foundation would be. You had basically 2 choices: rely on local experience as to what worked and what didn't work, or install a deep foundation and then perform a static load test to the point of geotechnical failure to see how much load it could carry. And we now see that we have advanced things to the point where we're developing methods that allow us, with nothing more than a spreadsheet, to go from a shear modulus profile to a complete load settlement curve. However, in this extensive change that has gone on, it's nice to know that some things don't change. And one of the things that seems to be part of human nature is the desire to leave our mark on things. Certainly we know tens of thousands of years ago, humans would do things like leave their handprints on the wall of a cave or leave some markings on the wall of a cave. And it's nice to know, with all the other change that's happened at Kennedy Airport, that some things have not changed, and humans still feel the need to leave their mark on their work. Well, with that, I want to say thank you for your attention in this presentation. It's been a long presentation. There's a long history to Kennedy Airport. But as much as I've talked about in these past few hours, there is a lot more to be said. If you're interested in some of the things I've talked about, I've written a tetralogy of white papers that deal with Kennedy Airport and some of the geotechnical and foundation engineering lessons learned from Kennedy Airport. These are in PDF form and you can download them from ResearchGate at no cost. You don't have to be a member of ResearchGate to join to access these, although certainly you're welcome to join ResearchGate. I've also tried to show you just how interesting and special tapered piles are, and how significant taper benefit is, and how underutilized it is. Really, tapered piles are something I think we should be using a lot more than we ever have in friction and floating pile situations. I recently published a book that discusses tapered piles. It is available using print-on-demand technology worldwide. You can get this from any online bookseller. Here is the ISBN 13 number. So with this number, you could go to Amazon or Barnes & Noble or whatever online bookseller serves your part of the world and get a copy of this book. And with that, I bring this presentation to a close. And again, thank you very much for your time and interest. I hope that you found some professional benefit from this.